Good morning, everyone. Good morning and welcome to the first session of day 4. Professor Mahesh Kumar Jat from Department of Civil Engineering, Malviya National Institute of Technology, Jaipur will be delivering. He joined earlier. Let's see if he is there. I'll give him a call. Sir, good morning.
Sir, good morning.
Sir, good morning. Sir, there are just 48 participants. Don't know how. I have requested them on WhatsApp to start. If you want, we can start. By the time they'll start joining it.
As you wish.
Sir, thank you very much, sir.
Yeah.
So, sir, good morning. Sir, there are other students of yours also. Good morning, sir. Good morning.
Sir, good morning.
Sir, good morning. Sir, good morning. Sir, there are just 48 participants. Don't know how. I have requested to start. So, good morning, everyone, and welcome to the 4th day of the FDP on advanced applications of remote sensing and GIS to be scheduled from 10th to 14th of February. So, welcome to the first session of day 4. Professor Mahesh Kumar Jat from Department of Civil Engineering, Malviya National Institute of Technology, Jaipur will be delivering. Sir will be having 2 sessions back to back. First session will be on applications of remote sensing and GIS in hydrology, and second session he'll be delivering on applications of remote sensing and GIS in urban studies, which is basically assessment of urban heat island oblique use of remote sensing GIS for master planning or zonal development planning at Exton. So, sir, welcome, sir, and thank you for providing us a chance to listen you again. To all the participants, Professor Mahesh Kumar Jat is professor in Department of Civil Engineering at Malviya National Institute of Technology, Jaipur. Sir is having a vast professional experience way back from 1999. Sir joined as assistant professor in Department of Civil Engineering at MNIT Jaipur. From 2000, then sir was promoted to associate professor in March 2008. Up to 2018, sir remained as associate professor, and then sir became professor in Water Resource Engineering Department of Civil Engineering at MNIT Jaipur only. Sir headed the department from June 2018 to 2020. Sir is bachelor's in civil engineering from JN Vyas University of Jodhpur, India. Sir is Masters in Engineering in Water Resource Engineering from Department of Civil Engineering from MNIT Jaipur. Sir did his doctorate in Integrated Water Management from 2004 to 7 from Department of Civil Engineering, IIT Roorkee. Sir is having a scientific focus in the areas of urban hydrology, hydrological modeling, land use, land cover change modeling and predictions, integrated water resource planning and management, climate change and its impact on water resources, development of an integrated water management model based on optimization of the optimal integration of supply and demand, land use, land cover change, and its impact on climate land use planning, and applications of geospatial technologies like remote sensing and GIS. Sir is having more than 55 publications in international peer-reviewed journals. Sir is having 4 books in contribution, and there are 4 book chapters also. Sir has delivered various invited talks in almost 56 conferences which are related to poster presentations or workshops. Sir is having a like H index of 16 and I index of 26. Sir has supervised 9 PhD which are awarded and 6 are in progress. Sir has more than 35 MTech under his supervision. Sir is having a vast experience of research funding. Full list is available on Sir's individual website. Sir is having a vast experience in research project management also, which are some of them I'll be talking about. In 2008 to 9, Sir did a work on water management plan of Jawahar Navodaya Vidyalaya Patola as a project team member. From 2004 to 7, environmental assessment and monitoring of DPIP project, World Bank project, project team member. Then from 12 to 15, assessment of climate change and its impact on urban hydrology, Indian perspective as a project team member in national coordinated project. From 2013 to 18, FIST DST project on development of water technology center as a project leader. From 2017 to 20, climate change impact studies of Rajasthan area, basically areas of inland drainage and Mahi basin, as Ministry of Water Resources, Government of India as a co-project leader. From 2018 to 21, development of experimental watershed and hydrological modeling of for improvement in performance of watershed intervention works as a project leader. So there are other projects also which are is a detailed list. So I welcome you, sir, and thank you very much for providing us time from your busy schedule for the benefit of the participants of this FDP. Thank you, sir.
Thank you, Pamar sir. And I hope my voice is audible.
Yes, sir.
And thank you for inviting me. Really, it is always good for academic people to interact with for academic causes. So I'm really thank you, and I will be happy to really interact with the students, and it's a both way learning. I will also learn from the participants if we go for an interactive mode. I'm really talking about 2 topics. Of course, they are related, very much related. Like I'm talking about remote sensing and GIS and their applications in hydrology and urban like studies. So hydrology, like remote sensing and GIS, I'm not going into detail about these things because probably you have already gone through it. So I will be talking to the only application part. But please feel free to interact when you have some doubts, like how these things are done in GIS, or how remote sensing is contributing, or how GIS is contributing. I will be happy to link with the GIS and their tools. Because while you are discussing an application, you will be more focusing on application part. And sometimes these technologies which are supporting those applications may be in the backside. So please feel free to discuss it. Okay, and always it is good that we should move in an interaction mode, because we can discuss the doubts and we can discuss more problems. So please feel free to really ask the questions in between. You can always stop me. As I said, that hydrology is a basically special phenomena. Special phenomena means, as far as hydrology is concerned, at some point or every point, something is happening. At some point of time, it is happening, and a lot of, you can say, different type of processes are happening. And those processes, which we can call it the hydrological components. So they are happening at every location, and they are also interacting with the surroundings. They're also interacting with the earth surface and other type of things. So really, spatial means we can think of the information or the data that is happening on the space, and if the space and their characteristics, okay, they are quantified, they are you can say their information is created in digital domain, and that information is very relevant and useful in hydrological assessments, because hydrology is happening on location at some point of time. It is interacting with the surrounding environment, and it have the relationship with the surrounding environment, with our surface and surrounding environment. So it means it is very important for hydrological assessment, and all the phenomena which are really have some influence or happening on the surface, and which are influenced by some characteristics of different objects and locations, and those locations are also affecting those processes. So for all such things, I think spatial technologies like remote sensing, GIS, they are very useful. And most important in hydrology is that using GIS and related technologies like remote sensing, okay, we can introduce, or we can incorporate the spatial and temporal variability of catchment characteristics into hydrological processes, in the assessment of hydrological processes. So by this, we can reduce the uncertainties, which is otherwise not possible with the conventional technologies. So that is main, you can say, very important aspect of using spatial technologies. So I will be discussing few, like again, application examples, hydrological modeling examples, assessment examples. So please, I will be happy really to interact. So I'm sharing presentation. Please let me know if you are getting it in the correctly.
Sir, it's visible. You can do the full screen, sir.
Okay. Okay, so now you are getting this?
Yes, sir, we are getting this.
Okay, so applications, as I just mentioned, that in surrounding to us, almost everywhere, everything that happens somewhere at some location, and sometimes which activity is happening where and how that activity is related to that location, it is very critically important. So in this, all activities, since they are happening on the space and they have influences of that location, such data and information, we call it geospatial data and information. And remote sensing and allied technologies like spatial data capturing things, satellite-based positioning solutions, UAVs, LIDAR, or GPR, many more, you can say, such technologies. They are helping in capturing the geospatial information, and that information can be stored, can be captured, stored, managed, and analyzed for different sort of problems in GIS. So the combination of spatial data capturing technologies and data analysis technologies, image processing technologies, combinedly we call them spatial data analysis techniques. So it means the data and information, wherever the location is having some influence, it is really critically important and very necessary to solve different problems correctly. I am using the word correctly because always, without remote sensing also, or GIS also, we were solving those problems, but we can solve them in better way with less uncertainties. That is the advantage with the spatial technologies. So the spatial data, as I said, that is spatial data is translate it indicates towards locational information, and sometimes we simply understand the locational information in terms of the maps. But spatial data is much more than the maps. Because always what is the different components or different type of things, like where we are living, different phenomena which are happening somewhere at some point of time, different activities which are especially dependent, how we travel, which route we should follow, and where we should locate different facilities, where we should locate the infrastructure projects. So all these are especially dependent, and everything is happening at a particular given location. So the spatial data is really, really very important, and spatial data combines three different aspects. One is location, means reference location with respect to selected coordinate and precision system. Then it may have the characteristics, which we call them as attributes, and it also sometimes captures the temporal information as well, like how the state of any object or phenomena is changing with respect to time. That is also stored in geospatial database. So these are the three, you can say, the main aspects of geospatial data that we need to consider, and we use in different things. Geospatial data, they are required in almost all, you can say, sphere of the engineering and natural resource management, and many socio-economic problems as well. Like geospatial data is required almost in all civil engineering projects for their planning, designing, operation, and maintenance. Facility management, this is an upcoming area where geospatial data sets are used in a big way, like managing big infrastructure projects, railway network, highways, basically big, you can say, operational, and any type of canal network, basically you can say the sewerage and water supply networks. So facility management, this is an upcoming area, and GIS is very critical for successful and optimized operations of projects. Telecommunication, we also use in the telecommunication to identify the locations, optimum locations of telecommunication towers, their facilities, their coverages, okay, to investigate the shadow effects. So in many areas of communication as well as geospatial technique and the analytics, they help us. And military, like in military, for logistic planning, for target detection, for many things, okay, we use geospatial data things in weather, in urban planning and development, because in urban planning and development, there's another area where remote sensing or spatial data things, they are contributing a lot. And we can do a lot of planning, design, and such planning activities, development activities on using the geospatial technologies. Then natural resources monitoring, their exploration planning, optimum utilization, disaster monitoring and management, hydrological applications, and insurance sector. So these are the, in almost all those areas nowadays, we people are using geospatial data things. And when the geospatial data, when it is combined with data analytics, big data analytics, it basically make available a lot of opportunities, possibilities to identify the hidden information from the very large volume of the data sets. We can identify, we can extract what are the different patterns, hidden patterns which may be there, which is otherwise not possible, complex interrelationship with respect to time and space. So big data analytics with the spatial data, okay, we can really, we can extract a lot of value-added information, which is from the simple means it is not possible. And sometimes we need particular information in a particular way, in a desired fashion, desired pattern, desired form. So those GIS or these technologies gives us capability to mine the data, a lot of spatial data that have the spatial as well as non-spatial data set, and using data analytics and data mining techniques, we can prepare, we can extract information to present in a particular way. Like some from the same database, information is sometimes required in different way for the urban planning applications, and the same information may require differently for the highway or for construction of railways. So what need, in what form we need, that sort of information can be produced from spatial data sets when it is combined with the other data analytics techniques. Now, geospatial data analytics or data analytics, this helps us in really determining patterns and in importance of like on data sets in terms of the distance, like how the distance is influencing a one particular phenomena from a one particular point. We can investigate the proximity effects, we can investigate contiguity and affiliations that are hidden in massive data sets. So these are really, nowadays you can say it is a big and coming up area that producing a lot of jobs and the business of billions of dollars, and very useful. It is making lives basically simple. Then, so geospatial data is we use them like preparing the information and developing know-how about the areas, about the objects and phenomena. Then we use the geospatial data for planning of infrastructure projects like roads. We investigate a lot of disaster monitoring, their assessment. We can go for adaptation and mitigation measures. It also helps us in socio-economic problems like crime analysis, what about disease surveillance, locating the facilities, health facilities or any public facilities, their optimum utilization, insite selection. Okay, so these are important things which we can do from this spatial data sets. Now, locations are sometimes very important, because sometimes we need to relate the locational influences into different phenomena, like why the flood came more frequently at a particular place, why the groundwater of a particular area is polluted. Okay, why so these are the basically influences, locational influences, which are influencing or affecting the different phenomena. So the locational influences, when you need to consider in monitoring or solving some problems, geospatial data is the only solution, or it helps. When the geospatial data with related technologies, just like you can say the models, mapping tools, okay, they make them more versatile and more useful. I request
I request all the participants to kindly keep themselves mute throughout the session, unless until you are having some question related to the topic. Kindly don't unmute yourself.
So allied, you can say sciences are like interaction models, where we integrate spatial data with other type of processes and models to solve different sort of problems, which may be physical in nature, biological or social sciences related. Then the geodesy and surveying, they provides us geodetic control and detailed locational framework. They provide us a framework to collect the data in a generalized form. Cartography, map, geospatial information, and GIS, they are used to model the geospatial information for different applications. Satellite and other type of, you can say, solutions, they helps us in capturing the geospatial data sets. So bigger general list of, you can say, geospatial data collection and analysis techniques is this, that geospatial data can be captured from conventional surveying techniques, from electronic distance and direction measurement techniques, satellite-based positioning solutions like GNSS technologies, then remote sensing technologies like variety of in active and passive remote sensing systems are in operation, from where we can get the data. IoT and sensor-based technologies, which are used to capture the data in real time about the different objects and phenomena, like discharge measurement, soil moisture measurement, meteorological parameter measurements. So a lot of things. Laser-based spatial data collection techniques like basically scanners, laser distance meters, LiDAR. Okay, this is a basically photogrammetric application-based technology, which can be used to generate three-dimensional information. Unmanned aerial vehicles to have the ultra-high resolution spatial data. Okay, then ground penetrating radars to capture the subsurface information, terrestrial laser scanners, they provides us three-dimensional data at a very high resolution. Image processing and target detection technologies, a lot of image processing techniques, enhancement techniques, filtering techniques, different type of mathematical algorithms. When integrated with these image processing technologies, we can extract different informations. Then GIS and big data analytics technologies. Okay, so these are the big, you can say, umbrella of or a general list of geospatial data collection analysis techniques, which is nowadays we people are using for different applications. Now, let me just go through the about remote sensing, because we are talking about the application of remote sensing GIS, and in hydrology or in any, you can say, phenomena which is somehow influenced by Earth's surface or geography. Okay, remote sensing can help us in capturing the variety of information. Simply, this is not about the location or a dimension or cartographic, you can say, map preparation of a particular object and phenomena. No, remote sensing and allied technologies can be used to capture the biophysical information. That is very helpful. And another very important aspect is from the physical measurements. If you want to capture the certain information and data, that is only possible at certain finite locations, measurement locations. So whatever data you are capturing from manual means or by other means, they are point data sets. But many areas, like in all the phenomena in hydrology and many more aspects, okay, they are aerial in nature. So the remote sensing helps us, giving us directly or indirectly many spatial data or information about many biophysical variables. Like a few of those information we can capture, and related systems or programs which are available to capture those information is like the biophysical variables, XYZ location, geodetic controls, and XY locations from orthocorrected imageries. So geodetic control means reference system. So all data set in digital domain from remote sensing we can get with the coordinate and position system. And you can get this sort of information from GNSS systems, global satellite navigation systems. Then we can get from the variety of satellites, like big list is available from Landsat to IRS satellites to very high resolution satellites like GI and GeoEye and WorldView. And of course, in active remote sensing domain, radar or RESAT or SAR or RadarSat. So a lot of, you can say, options are available. Another type of biophysical variable that we can get is topographical, three-dimensional topographical information and bathymetry. Bathymetry is nothing but you can say, bad information of water bodies. And that can be obtained from digital elevation models. Topography information can be obtained from DEMs, and bathymetry can be obtained from digital bathymetry models, DBMs. And these two things, topography means three-dimensional height information, that can be obtained from, of course, from GNSS systems. We can get from the stereo images that can be captured from the satellites, and that can be captured from LiDAR, UAVs, and a lot of other type of options are available. For bathymetry, we can use the sonar, bathymetry, LiDAR, stereoscopic aerial photography to capture the three-dimensional information of riverbeds or some water bodies when they are clear. Other biophysical variables are like vegetation. We can, nowadays, we have developed a lot of sensors and remote sensing programs where we can capture the very particular information about the vegetation and biomass. Like we can capture the chlorophyll, variation of chlorophyll that is available in the plant leaves. We can estimate canopy structure that is related to vegetation, their height. We can biomass derived from vegetation indices, absorb photosynthetically active radiations, epitranspiration. This epitranspiration is again very important. And when you want to plan the irrigation and you want to save a lot of water, or you want to enhance the irrigation water use efficiency, then correct estimation of evapotranspiration is very, very important. And nowadays, remote sensing is helping us to get remote sensing at a very desired temporal interval and over a very large areas, because whatever the better means or correct measurement of evapotranspiration is very difficult, and there are costly affairs. So nowadays we can rely on remote sensing to estimate evapotranspiration. I am presenting a case study that how satellite data can be used to estimate the evapotranspiration. Then we can another you can say biophysical variable that can be captured is surface earth surface temperature, about land, water, and atmosphere, and the remote sensing systems which helps us to get these biophysical variables are Ester, AVCR, GeoIS, Hyperion, Landsat 8 thermal infrared bands, MODIS, and airborne thermal infrared you can say sensors. So we can get it. Another biophysical variables about the soil and rocks. We can nowadays we are able to, using the middle infrared bands, we can measure the soil moisture to a certain depth. Then we can using remote sensing, we can use the mineral, we can identify the different type of rocks, and indirect you can say indication about the mineral compositions, taxonomy, hydrothermal alterations using these data sets like Ester, MODIS, and Landsat, Ester, MODIS, airborne satellite, hyperspectral systems. They can be used to get these things. Then surface roughness. This is very important for estimation of evapotranspiration and to estimate the aerodynamic part of operation evapotranspiration. So we can get from the satellites about the information on the surface roughness. Then we can have a lot of information we can capture about the different biophysical variables related to atmosphere, like aerosols, cloud friction, like what is cloud density in the atmosphere, precipitation. We are using now as a radars, a lot of radars, and that we are getting the aerial data about the precipitation that is otherwise not possible. We can determine the water vapor, we can determine the concentration of ozone, and we can do all these aspects, a lot of these data sets in the climatic studies. Then another biophysical variable, the information about which can be obtained from about the water, like what is the color of water, surface hydrological, like in rainfall runoff modeling things, we can determine the sediment load in the water. We can determine the extent of you can say chlorophyll that is available in the water bodies and dissolved organic matter. And these are the different payloads and remote sensing programs which can potentially used to extract directly or indirectly some of these biophysical variables. Then about monitoring and assessment of snow and ice extent. Okay, a lot of you can say on remote sensing and GIS, the remote sensing payloads are available, and these are the only solution in case of the natural disasters, also like volcanic effects, like floods. Okay, we can use these things to obtain about the information, the temperatures, about the gases, about flood extent, okay, from satellite data sets. Then we can get land use land cover information. Of course, this is the main use and application of in the hydrology domain, in urban and master plan, you can say urban studies. We can extract temporal land use land cover information at a variety of resolutions, and that land use land cover information is required for all type of engineering applications. We can get a lot of data about vegetation, crops, like for the health monitoring also. We can use a lot of data sets and different type of payloads which are available. So these are some of, you can say, the biophysical variables. I'm emphasizing it because sometimes we get confused that remote sensing and allied technologies, they are mapping technologies only. No, we can get the reference information about a lot of geophysical, you can say, phenomena and variables, and which are biophysical variables, which are very important, critically important for different phenomena and the solution of different problems. And advantage is that we are getting aerial coverage of these variables, which is otherwise not possible with the manual means. So that was the main areas of remote sensing related technologies, that how we can capture the information about different type of biophysical variables, which may be above the surface, on the surface, and below the surface, using different sort of remote sensing technologies. Then specifically, because our talk is focused on hydrology, so remote sensing and GIS and related things, they can be used in hydrology in capturing the watershed characteristics. So remote sensing can be used to capture the watershed characteristics, because without watershed characteristics, we cannot handle the hydrology. We cannot assess, or we cannot study the hydrology. So for correctly study of the hydrology, we need to capture the catchment characteristics, and catchment characteristics include land use, land cover information, soil information, topographical information in terms of elevation, then soil moisture estimation, vegetation estimation, water quality estimation, surface water resources inventory, their condition assessment, rainfall modeling, then groundwater recharge, infiltration, soil erosion estimation, then reservoir sedimentation studies, watershed development planning, and irrigation scheduling and irrigation planning. So these are the many areas where some or more part of these aspects can be solved using remote sensing and related technologies. So in hydrology, the basic and the initial you can say exercise or application is that we want to capture the catchment characteristics from remote sensing and related spatial data collection techniques. Then we create a digital watershed or digital catchment in terms of different GIS database layers and thematic layers in GIS. So our first step is data capturing about catchment characteristics, then creating a digital catchment or watershed by capturing the different thematic layers. And these are the typical thematic layers which are created for catchments in watershed for any hydrological analysis. So I'm just now discussing some of, you can say, advanced case studies related to hydrological applications where remote sensing and GIS are used. As I have given the example that for a solution of many problems, we try to integrate remote sensing and GIS and related technologies with the interaction models. Okay, like one example I'm demonstrating is use of SWAT. SWAT is a hydrological model that is based on GIS. So it means it works on as a backbone is the GIS. And so the data is captured from remote sensing technologies. Those data sets are converted into GIS databases, and then hydrologic models, they are parameterized from the database that is captured, and it is calibrated, it is validated, and then hydrological processes or water balance can be correlated, can be you can say relationships can be established from on a location basis, and we can understand that how your watershed or your catchment is behaving, how it is responding, okay, with the external stresses and external environmental consequences like climate change. So I'm just presenting a case study where remote sensing and GIS is used to model the hydrology, and modeling tool was SWAT. So this is basically extent of catchment, and that is Jessamine the lake and the small artificial lake that is available in Udaipur district, and this is part of Mahi Basin, and it is around 52 kilometers from Udaipur. And this is basically lake, and this is here artificial. There's a hillocks in both the sides, and in between hillocks it was an artificial dam. Small dam was created to create this artificial reservoir. It is also called Jessamine Lake. This is a big lake, and this is providing water supply to the Udaipur city and many more villages and towns on the way. So this is very important, and this is a part of Mahi Basin, and it is lying in the central sort of climatic zone, and general topography is hilly, and it is located between the 73 degree longitude to 74 degrees and around 24-degree north latitude. So the catchment of this my Jasmine Lake is around 18,000, 1,84,960 square kilometers. So big hectare. So big sort of, you can say around, this is 1850 square kilometers, and average rainfall is 570 mm, and temperature is around 27 degrees. So as I said, that first step in any hydrological modeling, you can say application, is that we need to capture the spatial data about the catchment characteristics. So that was the first step. Again, we have followed it, that using the different sort of spatial data collection techniques like Survey of India available maps, like Survey of India toposheets, satellite images from satellite-based positioning solutions. Okay, we have captured the data, and then second part is basically and mind it, GIS is helping a lot, because while you are collecting the data about catchment characteristics, somehow data set may be available in the form of tables, in the form of maps, and those maps may be in the different formats. Some are hard copy maps, their scale is different. So remote sensing GIS, it is really giving us a capability to combine, okay, and integrate the data is available from the diverse sources in different formats and different resolutions into common standards. So that is the role, big role of GIS. So that was the first part, we have followed it. And so after the capturing the data, we have created a GIS database. And the GIS database includes like watershed characterization, means there are watershed boundaries that is passing through the rays. So to delineate watershed, essentially we need elevation information. So elevation information is captured from the digital elevation models that is prepared from stereo satellite data sets. And further, the elevation information was conditioned, okay, by integrating the local, you can say, depressions, drains, water bodies, and water divides. So reconditioning of the DM is very, very important. And some of the information that is captured from certain toposheets was also integrated to recondition the digital elevation model. So that was done as the first part. So once it was done, then in the GIS, again, we have characterized the watershed. Watershed like delineation, the boundary, delineation of drainage system, and calculating the morphometric parameters for that catchment, like drainage density, and many other type of information about the catchment. So we have verified the larger drainage system with the drainage system that is available in Survey of India toposheets, and it was refined. So that was the part of watershed characterization that was done from the elevation information that is captured from different sources, from available Survey of India toposheets, from the DMs that is captured from stereo images. It was reconditioned. Then another type of basic layer is like, where are the water bodies, what is their extent, what are the small you can say ponds or small check dams or dams which are available in the catchment, their location, their small catchments, where their interventions are made. So that information was captured again from the satellite images and from the field data sets. Then we have derived other type of topographical information from the DM, like slope map, the direction of slope, okay, steepest direction of flow, like in which direction the water will flow when the precipitation happens. So direction of flow. Then we captured the land use land cover information for different years, because this was a modeling exercise. Okay, and we need to calibrate the model for a long-term data set. So we have captured around 10 years of data set in an interval of 3 or 4 years, from 1981 to 2018, 17, 18. And we have captured the, you can say, land use land cover information for different years. And in capturing the land use land information, standard image processing, you can say, process was used, like understanding the image, identifying the targeted land use classes, then training of the classification algorithm, then classification, then accuracy assessment, and then so that was the standard image processing process that was followed to capture the land use land cover information. Then contours, reduced levels, we have generated, we have the groundwater piezometric wells. So we have created their point data sets, and then we created the extent of aquifer, and through the litholog information, we have created the basically aquifer, like how the aquifer is varying in that area, what type of subsurface information is. So all those things are created in GIS. Then we have captured the position of rain gauge stations in the catchment and surrounding of the catchment. And then we have captured, integrated the rainfall data of 20-30 years, and that was attached as the attribute information from those rain gauge stations. And then the interpolation techniques were used to convert that point data into aerial data sets. So these are the process by which the data set and digital data set was captured about the water set. And so we have created in the form of different thematic layers, we have created, or we have extracted, basically we have prepared digital Jessamine catchment in GIS. And this is basically slope class values, like what is how the different area can be classified based on the slope. These are the range of the slope that, and slope is varying from 0 to more than 30%. So the area in the different slope classes. So this is usual data creation. This is like a stream, water bodies, and drainage network. And this stream order was assigned, and this is the morphometry, drainage morphometry, like what is the count and length of different order of streams. And then this is the soil map, where the soil texture classes are assigned on the basis of the space. And this is the aerial distribution of different soil texture classes. Then this is different type of small dams which are lying inside the dam and their catchments. And these are the satellite images from 1981 to 2018. At the different interval, 3-4 year interval, we have captured the satellite images. And these are the false color composites of like 1981, 87, 90, 93, 96, 99, and 2002, 5, 8, 11, 14, and 17. So these are false color composites. And these are the classified land use land cover information. That is, again, using the supervised classification algorithm and later on defined through knowledge-based classifier. So these are the land use land cover classes which are obtained for the different years up to 2017. And that, as I said, that through the stratified random sampling, the test pixels were selected for the catchment, and then their land use land cover classes are compared with the reference data sets. So in this way, we have obtained the classification accuracy that is satisfactory with the medium resolution data sets. And then, so once your digital catchment is ready, we have basically conceptualized the hydrological model, okay, using on the top of that GIS database. So here, basically, the SWAT was used, and we have parameterized the SWAT. So SWAT is working on a cell basis, means different hydrological algorithms are working on cell basis on GIS database. So that is a program code that is written, and that is called SWAT. So basically, it is using in GIS only. It is working on the GIS on a cell basis. So this is overall modeling framework of SWAT and the different steps in which model was set up. It was conceptualized. So the first step is, this is water set characterization. The second step is basically segmentation of whole catchment into a smaller hydrological response unit, HRUs, as a function of land use land cover, soil, and the slope. So these are the three parameters, and after the reclassification of these three parameters, because already we have these three digital layers, they are reclassified, and they are overlaid to generate the hydrological response units. And around more than 7,000 HRUs were basically extracted for the whole catchment. Then meteorological information like precipitation, solar radiation, relative humidity, wind speed, temperature, all these meteorological parameters which are captured from IMD and which are assigned as attribute information to the rain gauge station thematic layer, where those layers are converted into aerial data sets, and which were again supplied, they are assigned on a cell basis to each SRE. Then, so this is the meteorological data, this is interpolation here, and it is assigned to the cell basis. So then we basically, so this is the step where setup, SWAT was set up, means necessary parameterization of SWAT was done from these 3 steps. Then appropriate, you can say, model parameters were selected for calibration. We did a sort of sensitivity analysis to determine the relative influence of different variables on catchment behavior or water balance. And out of number of parameters, then we identified through the sensitivity main number of parameters which are more significant, and where we have calibrated them with respect to by simulating the hydrology of the catchment, and then comparing the water balance parameters with the observed data sets at the adjustment lake. And then those parameters, selected parameters, are calibrated. Then the model was validated using the different input data sets, and it was again compared with the observed data set. And once we are satisfied with the calibration, then our model was means ready for simulation. Then we have simulated the hydrological behavior of Jasmine catchment to investigate the different effects, like effect of if the climate is changing, then how it is affecting the hydrological response of water set or behavior of water set. And if land use land cover, if we want to investigate the effect of the land use land cover, then the hydrology was simulated by changing the land use land cover information with the constant meteorological parameters. So all these things are done in GIS. So mind it, this is a perfect example where remote sensing and light technologies are used to capture the digital data about the catchment, and then those data sets are integrated to create watershed characteristics in GIS. Then hydrological model was set up in GIS on a cell basis. It was parameterized, it was calibrated, and then the hydrological behavior of watershed was simulated corresponding to different meteorology, change in, you can say, climate meteorological things with respect to different climate scenarios, and the different land use land cover change scenarios were also investigated. So this is the overall methodology of that study. And so this is the conceptualization stages, the first step. And the model conceptualization include model domain definition, means like definition of extent of catchment. Then space discretization, like dividing the whole catchment into homogeneous HRE units. Discretization. Time discretization means with respect to time, that what is their time step where the hydrological processes were simulated. Then model was parameterized from the GIS database. Then different algorithms were selected to simulate or to estimate the different components of hydrological cycle, like infiltration, evaporation, epitranspiration, and those. So then selection of simulated time step, that at what time, like rainfall runoff conversion time step was like 1 hour, or droughting is 15 minutes. Then water balance is on daily basis, on monthly basis. So like this. Then the selection of validation period, calibration, so warm-up period for the just to test the model, then calibration period and validation period. So all those things are part of model conceptualization, which was done. And primary objective of model conceptualization, it is a process in which watershed characteristics are assembled in a systematic way to describe the rainfall runoff processes throughout the catchment. So again, that was done from the GIS. Like this is the model domain, you can say, definition and space discretization. Then this is basically different time domain discretization. and other parameter like selection of calibration, validation period, and all selection of algorithms. Okay, and then finally, after you can say definition of conceptualization, we can run the model, we can generate the water balance component, like what is the stream flow, what is the base flow, what is surface runoff, what is recharge, what is ET, precipitation, or evapotranspiration. So all those components can be estimated on a cell basis, on each SRU, okay, with respect to different time, we can get this information. So now you must be understanding that how the spatial and temporal variation of catchment characteristics are introduced in your calculation process, so that we can reduce, or we can you can say avoid the basically uncertainties because of unknown consideration of spatial and temporal variation. So this is a basically distributed model. This is a sort of physically based distributed model, and GIS and remote sensing, they helps us in incorporating the spatial distribution of different catchment characteristics which are influencing. This is also helping us in relating the catchment behavior with respect to location, like on different locations which are represented, or which are, you can say, represented by different type of soil, different slope, different type of land use, different type of, you can say, other characteristics, how these characteristics are influencing the hydrology. That is related only when we are able to capture the hydrological components and then in the same location, and then these things are related with each other. So that is helping us in quantifying the spatial relationships with the hydrological phenomena, and their spatial influences are incorporated into your hydrological computations. So if you have any questions, you are welcome. So in any part, how the GIS was used, and what are the different, you can say, even algorithms, we can talk about hydrology if somebody is interested. So up to now, if you have any questions, you are welcome. Any questions, please?
Sir, one more thing,
Yeah.
like from my side, because there are 2 continuous sessions, so you can tell me the time when we should take a break rather than continue, because 4 hours speaking continuously is very difficult.
Yeah,
so we can have a break of 15 minutes whenever you want.
Okay, sure. I will take, once we will be winding up
All
this.
the participants kindly engage in discussion.
So
Yes,
please feel free to really discuss things. If you have any doubts, any questions related to these aspects, we can discuss. Or even you can ask the questions on chat box. I will be happy to answer. So one question is coming up: can we find the depth of heavy metal contamination from remote sensing images? You see, directly, since from the remote sensing, this is asked by NR Gore. So basically, heavy metals contamination in water. You see, directly, what is the level of water? It may be available, groundwater may be available, say 20 meter, 30 meter, or more depth. So directly, we cannot capture any information from remote sensing. We can get some information from the GPR, like ground penetrating radars. So when we scan the subsurface, so because that is again working on the same sort of technology, when electron radiations, they are interacting with the different type of, you can say, formations below the subsurface, and if there is a change in substrata or concentration or water or something else, we can get the signatures. We can get that, okay, this is difference is coming up. And then those differences in reflectance, when they are correlated with the other ancillary information, we can get some information about contamination as well. I hope I'm able to answer the question. So any other question, please? Okay, so let's move. Okay, one more question is coming up. How many observation points are required? You see, it's a continuous data. It's aerial data. Mind it, because heavy metals, we can correlate a change, or you can say change in signature of electronic radiation from the GPR on a cell basis, and with the like geological formations, what type of geological formations are there, that is also available on a cell basis. Then we can have some data of piezometric wells. Then we can correlate if we have some industry and how what is the, you can say, location or locational influences with respect to that industry. Then also we can have an idea about that whether this industry is influencing it or not. So all those aspects we can get it from on a cell basis. Okay, so so any other question, please? Okay, so let's move forward then. So this was the model conceptualization. The next class that we have basically data sensitivity analysis. Okay, so this was the period like from 2002 to 2004. This was used as a warm-up period to test the model, how to get a real-time satellite data set. You see, in real time, there's data is not available. Satellite data is not available because all satellites, they are rotating in their fixed orbits around the surface. So we know that at what time they are passing from a one particular point. Okay, so we can get the data of those points only. Real time means like when it is capturing and when it is transferring on the ground, that the some time window is required because data is captured from the satellite. It is pre-processed by the capturing agencies. Like the data has to be, you can say, corrected for radiometric and geometric errors. Then only it has to supply to the users. So that time is required. But of course, if you know the satellite passage at what time it is passing, you can pre-order the data that okay, you need the data of this date. Okay. Then if you want to make some physical measurements on the site, you can do, and later on you can get the satellite data and you can correlate. So that is possible. Okay, so this is warm-up period. So from 2005 to 2013, all the catchment characteristics, including metallurgy and observed, you can say, data and means observed discharge in the dam from 2005 to 2013. That period, basically for 9 years, it was used for model calibration. Model calibration, and then from 2013 to 17, after the calibration, we tested the model, okay, whether our model is simulating correctly or not. So these are the rainfall like amounts on the different dates, the maximum rainfall. So we are just presentation purposes, we have targeted because the rainfall in India is happening in the monsoon season only. Okay, so that is depicted from the diagrams that in a narrow window, some months, 2-3 months, the rainfall is happening. So this was the, you can say, model calibration. Then these are the different parameters, 20 parameters of the model, which are used in different estimation of different, you can say, processes, hydrological processes. So those are selected initially, and their sensitivity was tested by running the model for different years by changing these values to a certain range from the default values. Like certain default values, then a range is decided based on the literature reviews that what are the values were reported in literature. So we tested the sensitivity of the model, that how a unit change in one particular parameter is affecting their outflow. So you can say the relative change in output, model output, as a function of unit relative change in input parameters or these parameters, that was investigated to arrive at the most significant important parameters which need to be calibrated for that catchment. So that was done. So initially this was sensitivity was done, and this is the sensitivity results. So just you can see that p values and t statics. So if your p value for the 95% significance, if it is less than 0.05, then those parameters are significant, otherwise not. So this yellow briquette, these are the parameters which have been found to be significant for the different parameters. So because from such a study, or by using the two criteria, T statics and the p-values, okay, we have determined that which parameters are more significant out of those 20, and those should be further selected for calibration for different years. So these are some of the parameters which were finally selected, and model was calibrated for those models. So this was the range, and this is the optimum fitted values corresponding to those parameters. So these are 1, 2, 3, and 7 parameters. These 7 parameters were found to be significant, and these are their calibrated values. These fitted values, these are their calibrated values. Okay, and these are how the calibration process was fitted well. So these are the lower and upper 95% confidence limits, this green areas, and this red and blue is observed, and this red is simulated. So we can see that as the calibration process is corresponding to optimum parameters, calibrated parameters, basically your simulated results are following the trend of observed data sets for the different time periods. See, like they are matching the peaks. Of course, there are certain variations are there, but the trend is quite matching and the difference is not so significant. So that's why that was assumed to be calibrated. And then this is the range that how the calibration was for the different years. These are the p-bias values, which is less than 10%. So we can say that model calibration was satisfactory. Then model was validated for a different data set, which was not used for the calibration from a period of 2014 to 2018. And see the validation results. Well simulated results in the blue color, they are well matching with the trends of observed data sets. Okay, and this is perfectly matching. So and when they are plotted on a scatter plot, we get the basically R square value more than 0.8, and percentage p bias is less than, again, 10%. It is around 5.7. So it is indicating that model is basically performing satisfactorily. And these are the modeling results for a area of more than around 2,000 square kilometers. So this is quite satisfactory in terms of model calibration. So once this was ready for us, then basically we have investigated on cell basis. Now here, look at it. These are the examples that how the locational influences, they are tested. Means how your hydrology is affecting, or it is related with the location. So these two aspects are investigated on a cell basis. Okay, in one two cases are conceptualized. One is to investigate the climate change effects, and that scenario was conceptualized by considering the constant and the same land use land characteristics. And 1981 was used as a base year, and the land use land cover was you can say adopted for the base year and methodology of different years from 1981 to 2014. Then the hydrological behavior of the catchment was simulated. Okay, and because this is a long period, and it is difficult to, you can say, handle the data sets as a daily. So we have converted into monthly water balance, and then we have related that what is the relationship between change in meteorological parameters and what is it, behavior. Because during in the climate change, climate is basically we are ascertaining the climate change in terms of relative change in meteorological parameters over long range. So if you want to quantify the effect of climate change on hydrological processes, then we need to quantify that how unit changes in meteorological parameters, how they are affecting the watershed response. So that was basically tested for this case. Okay, and in the second case that was conceptualized, that how we can determine the influences of land use land cover changes if your meteorology is constant. So in that scenario, we have kept the meteorological information as constant for a base year, and then land use land cover was you can say adopted for the different years, that was obtained from classified satellite imageries, and Then again, calibrated model was used to simulate the waterside behavior. Waterside behavior means how the water balance is a function of these characteristics. Okay, and then they are related. So I'm just presenting the results. So in first case, see the water balance parameters which are used to define the waterside behavior. So like groundwater discharge, surface runoff, potential evapotranspiration. So these are some of soil erosion. These are the waterside behavioral parameters, which we are saying that waterside behavior is represented by these 5 parameters. So how meteorological parameters are changing, what relationship they have based on these simulated results. So we can say that like groundwater recharge is inversely proportional to the solar radiation. It is inversely proportional to mean temperature, maximum temperature, but of course it is proportional to the precipitation. Okay, higher precipitation means higher groundwater recharge, and these are parameters, because when solar radiation and temperature is increasing, lot of, you can say, evaporation, evapotranspiration will increase. So in overall water balance, when you lose more water in these processes, less water will be available for the runoff and groundwater recharge. So this is perfectly satisfactory results. Then for surface runoff, again, your temperature, solar radiation, they are inversely proportional, and your precipitation is proportional to the surface runoff. This is another, you can say, relationship which is verified. It means results are perfectly indicating that if your climate, if your meteorological characteristics are changing with respect to climate change, like if your rainfall is changing, okay, then it will change their runoff, groundwater recharge. If your temperature is increasing, it will adversely affect their hydrological behavior of a particular watershed. Then soil erosion, again, it is proportional to precipitation. If precipitation more, soil erosion due to runoff flow, that will increase. And wind speed, if your wind speed is more, soil erosion will take place more. And temperature is more, then also soil erosion will be more, because in both the cases, when soil moisture is less, then wind erosion will increase. When the runoff will increase, your water-based erosion will increase. Then PET, potential evapotranspiration, it is again proportional to precipitation, because when the moisture availability is increased, PET will also increase. When the solar radiation and the temperature will increase, your PET will increase. With the increase in humidity, okay, because increase in humidity means there will be less you can say vapor pressure gradient exists in the atmosphere, and it allow less evaporation, evapotranspiration. That's why relationship is reversed in this case, in case of relative humidity. Otherwise, it is proportional. So we can conclude from the results that of course climate is going to change significantly the major you can say hydrological components of a given watershed, and hydrological health of a watershed will be adversely, you can say, affected by the climate change. So that was another like case where we were interested in studying the watershed behavior as a function of land use land cover characteristics. So in this particular case, the methodology was kept at the base year 1981, and land use land cover of the different years hydrological behavior was simulated corresponding to different land use land cover characteristics. And you can see basically like agriculture. With the agriculture, like if agriculture is increased, PET will increase. This is obvious. Okay, more vegetation means more evapotranspiration. If vegetation is more, surface runoff will reduce. Definitely, it will reduce because your infiltration will increase due to vegetation. Your water will be trapped for more time on the surface. It will increase the infiltration. It will increase the evaporation and evapotranspiration. So these two results into less, you can say, your surface runoff. But groundwater recharge will increase, definitely. When you trap the water for more time on the surface, more time is available to recharge the groundwater. So groundwater recharge is proportional. Soil erosion is inversely proportional, because because when the kinetic energy of water is less, because velocity of flow of water due to vegetation will be less when you have a larger vegetation. So that kinetic energy will reduce the soil erosion that is induced by the runoff. So that's why, and also due to wind erosion that will reduce. So vegetation, that's why its relationship is inverse. Then dense forest, or you can say shrub. So how the forest, so this is results are similar to they are similar to basically with the agriculture, that your surface runoff and soil erosion, they are inversely proportional to the area of forest in a catchment, relative area of a catchment in forest, and groundwater recharge and PET will increase. Similarly, fallow land. So in case of fallow land, because PET will reduce. When the fallow land means there is no vegetation, or vegetative areas, cropped areas, your fields are now vacant. So less vegetation means less PET. So more runoff, okay, more soil erosion, less groundwater recharge. So the same thing is vindicated, or this is revealed by the results of the study as well. Then sparse vegetation. So in case of sparse vegetation, just look at it. Basically, like in this, slope of PET is very steep, whereas when your vegetation is sparse, your slope PET is less. So it means directly you can say that the vegetation cover, density of vegetation, height of the plant canopy, both are affecting your LP transpiration. So dense in terms of canopy, dense in terms of the vegetation, more PET. If it is sparse, less potential LP transpiration will happen. And similarly, it will affect the soil erosion, ground recharge, and surface runoff. Then water bodies. So this is obvious relationship for water bodies. Then trends between sandy. So the number of different land use classes, they are clubbed together, which are similar in nature, like sandy areas, open land, barren land. So they are combined together, and their combined influence is because in barren areas, we have the less vegetation. So obviously, more PET will be less. Okay, so that's why relationship is inverse. And in such areas, because when water will flow, it will flow with a high kinetic energy, so soil erosion will be more. Your runoff will be more because your response will be fast, because it will not retard by the vegetation, and it will have a less groundwater recharge. Then the mining areas, okay, and so these are the outcomes. So we can conclude from the study that really catchment as well as your metallurgy as well as catchment characteristics, they are very important for hydrological processes, and they are affecting and we can relate with the location basis. And this remote sensing GIS, these are the tools which can be used to investigate locational effects and to, you can say, determine the watershed behavior with respect to space and time, okay, in a better way with less uncertainties. Okay, so this was the hydrological case study. And for this first lecture, how much time I have so that I can continue this some more stuff. Time is available.
Sir, we can continue up to 11:45, and then we can have a break if you want.
Okay, so
if you want to have a break now, we can start.
No. Let's complete this first hydrology part, then we'll have the break.
Okay, sir. So, sir, 10 more minutes, sir. Then we'll take a break of 15 minutes.
Okay.
Okay, sir. Okay,
so
sir.
Any questions, please? If anybody have any questions, I will be happy. Even we can restrict it, and other than this case study, if you have any other question related to hydrology and hydrological applications or remote sensing GIS, I will be happy to interact. So we can keep 5 minutes later on to just discuss this, that what are the different questions or what do you have. So I will be, you can say, finishing talk at 11:40, and then we can have 5 minutes for discussion. If you have some questions, I may be happy to answer it. Okay, so I'm going for other study. Then later on for the same study, what we did is we try to formulate some mathematical relationships between these catchment characteristics and watershed behavior. So watershed behavior was quantified in terms of those variables which are used as a dependent variables like soil erosion, surface runoff, groundwater recharge, and PET, and they are related with the metallurgical parameters, and we have developed these equations. And later on, we have used these equations to develop an index to quantify the climate change effects on watershed. So that was some other time we can discuss it. So these are the equations I developed. Then I would like to really discuss this case study where remote sensing and allied technologies can be used to ascertain or to monitor the changes in topography, in hydrology of a particular given area. So if we are doing a lot of interventions in a particular area to improve the hydrology or to improve the agriculture or something, how those changes, whether it is positive or negative, they can be monitored, they can be quantified. So impact assessment of watershed development, how we can do from the remote sensing GIS technologies. So these can be done in different ways. Okay, so what changes watershed undergoes during and after watershed planning and development, okay, that is called monitoring and impact assessment. So I'm just going through, I'm giving the examples. So see the three examples, because watershed development is done for the wasteland areas where the land is degraded. So just see this example, like this is watershed before treatment, when the treatment was going on, the middle image, and this is the last one. So the hydrology of area was improved, a lot is improved, and see the comparison. So from the remote sensing, okay, really you can just monitor how things are unfolding and how we can compare basically. Then see another three, you can say, look locations, like this is stretch where a lot of landslides are happening. Okay, so it was treated, okay, it was modified during the treatment, and see the after the treatment, that is restored. So the whole area is becomes now nice. So just look at it from remote sensing technologies and allied things, we can really monitor that what changes after the intervention works can have taken place in case of vegetation, in case of how surface water bodies they are increase or decrease, water harvesting increase or decrease, okay, the condition assessment of the soil, what change in the runoff, what change in the soil erosion. So all those things, what change in groundwater recharge, these things can be really quantified using this technology, because again, we are doing all these things on a cell basis, on a location basis. Okay, so just look at it, monitoring the progress of conservation work using high resolution satellite images. So see the impacts. Okay, these are the two basically FCCs. So see, this is a farm pond that is constructed on land, piece of land. These are the contour trenches which are you can say excavated to reduce the soil erosion. So same can be captured. So see, this is the pond basically. This is the farm pond. Okay, and this red part is due to the basically algal growth, chlorophyll. That a lot of chlorophyll is visible. The pond may be some vegetation may be there. That's why this is reddish coming up. Then these are the contour trenches. Just look at it. These contour trenches are available. This is the actual photograph. So mind it that we can compare that whether the work is going on or not going on, how much work has been done, and what are the positive impacts. Like these are the farm ponds. This is a farm pond. These two are farm ponds. So automatically we can get this information. Even you can correlate with the field data sets. Like these are the field trenches, and the photographs are taken from the field. Like these are the trenches. This is the farm pond that is actually available in the area. Okay, then just see the satellite-based monitoring of field bundings. So this is the before field bunding, and the field bundings are done to reduce the soil erosion. Okay, so here in this particular area, there is no field bunds are available. Just look at it here. These lines are more clear, which are represented by field bunds. These are the lines which are giving us an idea of the field bunds. But here they are visible. So we can see that they are going on. Then another is see that these are the farm ponds before treatment and after the treatment. Okay, these are the number of farm ponds which are coming up, which is otherwise not available in these areas. So from the again remote sensing, we can monitor them. Okay, then monitoring the changes in vegetation cover using remote sensing images. So you see from the satellite images, we can generate the NDVI, normalized difference vegetation index. Even we can determine that whether your vegetation is increased or decreased. Simply you can take the temporal satellite images, extract capture the basically NDVIs and compare that NDVI of 2 time intervals, 2 time periods, and we can have an idea about change in vegetation. Okay, so this is before treatment and this is after treatment. So see the surface water bodies, the same area. So after like creating the water harvesting structures, intervention works, these are the lot of water bodies are created which is otherwise not available. Now see the water and see the increase in vegetation. Here a lot of vegetation is there and here less vegetation is there. So these are the positive effects and in the hydrology which are coming up from the watershed planning and treatment. Then also we can have an idea about the vegetational growth and different type of sediments which may be available in the water bodies. See the reflectance, different reflectance, and you can have an idea because we are getting different reflectance. They are giving us an indication about quality of water in surface water bodies. Like here, this third one is indicating that a lot of sediment is there in the water, because that's why the reflectance is we are getting from, because ideally we will get the zero reflectance if your water is clear and it is having good depth. So certain thing is clear cut indicating that a lot of sediment is there in the water body. And in these two cases, you can see a lot of biomass or a lot of, you can say, green vegetation cover is there. It may be algae, it may be some other type of vegetation. And this is maybe indicating the eutrophication problem in the water bodies. Okay. Then, so we can get some information from the reflectance and quality about idea of groundwater quality, or sorry, surface water quality. We can get in terms of change in reflectance in the particular bands. Like we can get the extent of surface water bodies. We can create inventory of surface water bodies through this index, that is normalized difference water index, and NDWI. And from the NDWI, we can obtain the extent of water bodies. See these two differences. So a lot of, if you compare this, these two, so you can get the June part, and this is NDWI. Okay, so see the difference. That other things we are not interested in other parts, so we are only interested in water bodies. So by processing simple ratioing of different bands, you can get the number of water bodies and their extent. Other type of information may not be relevant to us. That's why if you want to get the inventory, you can get directly inventory from satellite images, and you can compare from the 1 time to 2 time periods. You can have an idea about what has happened in hydrology, surface hydrology part of your catchment. Then we can have some idea about the, like this lot of, you can say, sediment may be there in the lake. Okay. And then we can investigate in the rainfall runoff processes that between 2 time periods, how runoff has changed. So actually between 2 time period, if you are changing the watershed characteristics, so only what will change, you simply, like let's sweat model, we see the example, simply you change the land use, land cover and climatic characteristics, and you can investigate the change in runoff response. So this is a methodology where land use, land cover, soil mop and slope, these 3 are potential changes may be there in case of watershed development. So simply you can simulate the runoff in pre-watershed development scenario and post-development scenario by changing these 3 GIS layers, and you can quantify the changes in runoff. Similarly, the soil erosion, change in soil erosion after their interventions, we can determine by simulating the soil erosion in 2 cases. One is before watershed development and one is after development, and only things will change that will, your drainage will change, your land use will change, your conservation practices will change. So these 3 aspects, you can change them in your post development scenario, and you can determine the soil erosion potential. And by comparing these 2, we can have an idea about the basically change in and mind it, all these things are done in cell basis, that all we people are doing in the GIS only. That's why we are relating the location with these hydrological processes. Okay, so in this particular terms, we can calculate. I have more, but due to time constraint, we now we should restrict ourselves. Now, please, if you have any questions, I will be happy to interact. So any questions, please. We can discuss it now for 5 minutes or 10 minutes. and then we can take a break.
Sir, one small question from my side only.
Yeah,
We
please.
keep on saying this maps as LULC maps. However, most of the times we keep on like driving these only land cover maps rather than the land use maps. So how many times, like in all the studies that I have conducted, the land use are rarely discussed rather than, and most of these studies only conduct these land covers only. So how justified is
both,
it?
yeah, both are different. Both are different, but many a times you are right that we cannot distinguish them, that, and we use synonymously in many studies, but both are different. You see, for a larger when context, okay, land use is man-made use of, you can say, the location or our surface, that is land uses, and primarily these are like built up agriculture, those things. In case of land cover, like natural cover, forest, and these things. So correct way of doing it is we should use both the terms simultaneously, land use, land cover. Always we should use both the terms, because like in hydrology also, both are relevant, both are important. Man-made alterations, they are equally very, very important. That's why we used to use the term land use and land cover both. And always all the maps, they are both. We don't have only land uses or we don't have the land use covers. We both. So that's why always it is correct is that we should use land use and land cover both.
This is more like presentation of yours. When we are doing master planning, we are more concerned about the land use at urban areas.
Yes. But land use, you cannot plan land use without considering land cover, because ultimately land cover will be converted into land use.
Sir, so can we identify land uses also through remote sensing?
Yeah. Yes, you can. Means what, like how you are making decisions of land use. You are using certain criteria. You are using some policy decisions. So simply those policies you need to, those decisions you need to, you can say, apply on a cell basis to decide land use of one particular cell. That's it. And you can do objective decision definitely.
Thank you, sir. Thank you very much. All the participants, any other question from your side is most welcome. Otherwise, we'll take a break of, let's say, 10 minutes.
Yeah. Any questions, please? Or what we can do is you can think of the questions, we can answer after coming back from the break.
Yes. Yes. So let's have a break of 10 minutes. We'll come back again, let's say 12 noon.
Okay.
So we'll have a break, sir. I'll stop the session.
Okay. Thank you.
Thank you very much, sir.
Thank you.
Hai chapter ko pag
Hello. Greetings, sir. Sir, welcome to the second session of day 4. And we can now start the session. There are various participants, now 84 participants are joined. So we can start the session.
Yes,
Sir.
yes.
To all the participants, Professor Mahesh Kumar Jat, Professor in Civil Engineering Department, Malviya National Institute of Technology, Jaipur. Sir will be delivering on applications of remote sensing and GIS in the second session. So, sir, welcome again, sir.
Thank you, Mohan sir. So let's start from the what like we're discussing. So if you have any questions from the last session, we can discuss it now.
Any participant whosoever is having any question from the
please
previous
unmute.
session also,
please unmute.
They can raise
yourself.
hand and unmute themselves.
Yeah. No. So then let's start a talk. I'm again. So in urban areas, similar to hydrology, because in urban areas are nowadays becoming more and more important, because with the aspiration of peoples are for better education, better employment, a lot of migration is taking place towards cities, and a lot of population is like living nowadays in urban areas. And I estimate presently more than 50% of world's population is residing in cities. So really, city planning, urban planning of cities, and other aspects of cities, okay, they need to be studied, and like services, public services, infrastructure planning, land use planning, okay, environmental like sustainability, natural hazard, different sort of, you can say, man-made hazards, their monitoring, their containment and mitigation, urban heat islands in urban areas due to the lot of conversion of pervious areas into impervious one. So these are the variety of the issues which are very important, and cities are more important because a lot of population is living there. Population density is very high. So more like people are residing, more people are under risk for a variety of, you can say, the consequences. That's why we really urban areas, and they are very important to study. One more important thing for urban areas is the conditions are dynamic. In urban areas, conditions are dynamic, like land use, land cover is dynamic. Okay, your meteorological conditions are changing. Daily temperature is increasing due to conversion of soft surface into hard surfaces. There are more chances of natural hazards or man-made hazards in urban areas, more socioeconomic problems like crimes and many more things. So really, they are important because things are dynamic and daily changing. So the temporal dimension is significant in case of urban areas as compared to rural areas. So that's why GIS it becomes more relevant to study GIS or related things, because to capture the temporal data or temporal information, spatial data of the cities, how they are growing, how different infrastructure is going on, what is changing, what is not changing, we require temporal, very frequent data sets. So that's why remote sensing is the only solution to capture the data repetitive. So repetitive coverage is possible from remote sensing, that you can even capture, even you can monitor on monthly basis or annual basis, which is otherwise not possible from the manual means. Like in which city, in which direction city is progressing, in which area more development is taking place, in which area less development is taking place. So all such things can be studied in urban areas. And probably remote sensing GIS is very much helpful in monitoring the urban sprawl, in urban growth monitoring, land use and cover changes, their impacts in planning, developing, or even master planning or general development planning of urban cities for sustainable natural resources. So these are the areas, upcoming areas where a lot of work is going on, and a lot of scope is there where these special technologies are very much useful. So I'm just from like how we can do. So I'm again discussing few case studies. I'm just discussing the scope. So please again feel free to interact. So I'm just opening a window so that what are the scopes? What, and you can even ask the question that how for solution of this particular problem, how we can use these technologies. So I'll be happy to interact for those aspects as well. So I'm just briefly discussing few case studies about one case study is related to target detection, that how we can capture the built up areas. One of my PhD students did research like from the satellite images, how we can capture the building footprint accurately, automatically, without manual digitation, by simply image processing, how we can extract it. Then I will be discussing a few aspects, one case study of like how you can study the sprawl, that is study from the Pune, and a few other aspects like presently in our institute in collaboration with the Department of Architecture and Planning, Dr. Nand Kumarji, we are doing some projects on zonal development plan. So I will be presenting a zonal development plan process, how it was done in GIS. Of course, I am not expert of planning, but how that was done in GIS, I will be discussing it in the form of a case study. So I'm sharing presentation. Please let me know if you are getting this. Okay, so I hope this is now coming up.
Yes, sir, it's visible, sir.
Okay. Okay, so as I said that this is line again very much relevant in case of topography, that almost everything that happens somewhere. Knowing somewhere something happens is critically important, and that is also very much relevant for urban areas. As I said, that this is geospatial technologies are more you can say important for urban areas, because a lot of population is residing, and a lot of you can say peoples are getting affected by every aspects of urban services, urban infrastructure and things. So the typical remote sensing GIS applications for urban planning, development and related aspects, they include urban sprawl analysis, cadastral mapping, land use management, land use land cover mapping, change deduction, change analysis, urban growth modeling, urban facility and their site selection. So this is another aspect where GIS, because making decisions about what type of public facilities are suitable and what should be their optimum location. This is an area where you can do this automatically in GIS that is free from personal biasness, and you can locate correctly on a technical basis. So that is very good thing you can do in GIS, like urban facility identification and their site selection. Zonal development planning, master planning, stormwater management, urban infrastructure planning, facility management, solid waste management, like identifying the waste disposal sites, identifying the routes in which we should carry the solid waste, urban heat island analysis assessment, and how we can do it. Basically, we did one of my students did a PhD in this area, where we did a energy balance modeling for cities, and we have investigated that how land use land cover change is affecting your microclimate, and what optimum adaptation mitigations can be done. Though of course it also helps us in dealing with the facility location, like facility location of health facilities, school facilities, and disease surveillance. So many more areas where we can use remote sensing and light technologies. Okay, so these are the broader areas of urban related applications. Okay, so I'm discussing few of the aspects related to this, and this is the endless list. Nowadays, even you can use any type of traffic planning, traffic management. So many things you can do. We can use remote sensing in GIS. So first of all, like how remote sensing GIS or these technologies or digital databases, they can help us in urban planning. So I'm just highlighting few points, you can say important points where one can think of using these technologies. And a lot of people are using them nowadays. Okay, so like urban planning is one of the main application of remote sensing GIS. Urban planners can use GIS both in spatial database, their analysis, and of course for modeling as well. Like analysis means like extracting patterns, hidden complex, you can say, information, then identifying suitable provisioning of facilities, provisioning of you can say circulation spaces, provisioning of parking lots, provisioning of, or you can say putting land use restrictions and all those things. We can do a lot of analysis in GIS, and you can do the analysis. Then application of GIS can vary depending upon the different sort of stages where and how we are using in different levels, different sectors, and of the functions of urban planning. We can use the GIS. So I will be discussing like in sector basis or different levels how we can use the GIS. So with and nowadays, because a lot of you can see improvements are taking place, a lot of GIS softwares are available in public domain as well, and GIS interfaces are very user friendly, so anybody can use it, and they gives us capability to integrate. Again, I'm using the word integrate, the different sort of information, whether it is available in different other maps. So you can integrate, you can overlay them, you can look into all different type of characteristics which are relevant to one particular location, and then you can make optimal decisions. So that all these things are possible in GIS only. Otherwise it is not. So then recent advances in GIS, we can use a lot of modeling tools, visualizing things, internet, and like web-based GIS things. Okay, for which help in a better planning in capturing the data set and for decentralization of these services. Okay, so main constraint in GIS is because the softwares are costly if they are not in public domain, and you need computational resources, quite good resources, and of course skills as well. Like if you want to use this as a only mapping tool, then it is a sort of AutoCAD. But GIS is not a mapping tool. Basically, GIS have inherent data analytics capabilities. That a lot of data, we can analyze the data sets, we can use the big data analytics, and we can solve the different problems in more intuitive way rather than simply using a mapping tool. And unfortunately, in planning aspects, still people are using, a lot of people are using it only for sort of mapping. But actual potential is in data analytics. So we should use it for analysis, for problem solving, for planning, for selection of provisioning, selection, site selection, okay, for those aspects. Creating scenarios, of course, in the scenario modeling also, this is very good. That depending upon the different policies, you can create different land use plans, different sort of, you can say, land use planning scenarios, and then decision makers can deliberate and can, you can say, finalize the optimum plans. So that for scenario modeling also GIS is very good. So benefits, what are the advantages of GIS using in urban planning? They are improved mapping, because GIS gives us capability to convert the same database into variety of presentations. Like same database can be converted into a particular presentation that is suitable for a particular application. Like in say road planning or infrastructure planning, you need a different sort of information that should be presentable in a particular way. But of course, in land use planning, some other like socioeconomic things or another things, we require the same information in different way. So that is basically very versatile in GIS. Then increased access to information, because you see GIS is very helpful in storing the large volume of spatial data. Like spatial data is having huge volume of data set, like locations, and thousands of different characteristics which are belongs to those locations. There can be captured. The data can be stored in a professional way, so that your data is stored with the safety, and you can retrieve the data at a very fast in a particular way. And you can put that a lot of, you can say, data queries in a different type of way, or different methods you can extract the different information. So GIS helps us in storing the large volume of data. We can manage it, we can manipulate it for different applications. And even nowadays, like in web-based GIS solutions, like we can use on the fly, we can use the GIS tools to create data, to analyze, and to generate the outputs. Improved communication with a unified system of data storage management. Okay, because data is stored in professional database systems, there is no chances of redundancy in the data. There is no chances of data dimensionality in the data. So we can remove the dimensionality from the data sets, and we can make the improved decisions. Even we can extract from a very large volume of data set, we can extract a particular information, that is putting a condition. Like for example, for example is like we have a revenue record of whole country, and suppose we want to identify for one particular government scheme for beneficiaries, and your conditions of beneficiaries are like that one should be belongs to a particular social group, he has to have the land holding should not be more than this, and like this. So identifying beneficiaries by putting such a condition is very difficult manually. But if you have a GIS database, such things can be done in seconds, okay, without any personal biasness. So that is the improved communication. We can extract data in a better way. Then increase quality and efficiency of public services, like data dissemination, data display, information dissemination, extracting the information, preparing your information. That is very fast in GIS. Okay, like revenue records. Nowadays, revenue records, a big program is going on from the government of India, where we are converting revenue records into digital reports. And nowadays, everybody can look just on Book Khata or Apna Khata sort of portals. Okay, in the backbone, there is a GIS that you simply write down your name or Khata number. You can have your revenue records. You can have the maps, plans of villages, their boundaries, their kasras, all things. So in backbone, that GIS is working, that we are mining the data, that whole database is stored on servers, and we are putting queries, and based on that, we are displaying the data sets. So that is the potential of GIS, that we are using them for better, you can say, efficiency in the public services. Then, as I said, that we can use GIS and digital data set for scenario generation. What if scenarios? We can put like for solution of different problems corresponding to different policies, we can generate different options, and then we can compare options in what if scenario sort of analysis, and we can determine more optimum solutions from GIS. Okay, so these are the advantages in urban planning, and because all urban planning related decisions are related to space, so that's why the GIS is the best solution for urban planning related applications. Another benefit is because improved mapping leads to the better access to maps, improved map accuracy, more effective thematic mapping, reduced storage costs. Because data is in digital domain, you need to create data sets again and again. Data updation is very easy. Like suppose for a city is developing, so you have the basically built up area. So tomorrow simply you need not to create again the built up area for so you can update the things. Whatever new changes are happening, simply you can change those parts, and that remains same. So your efforts of data creation, handling, storage, chances of deterioration, they are very less in case of a GIS-based planning. Improved analysis, you can do a lot of scenario related analysis. We can identify a lot of hidden patterns, complex patterns. We can relate multiple aspects to make a decision based on the location. That is that can help us for improved analysis. Better communication to the public and staff, improved quality services for speedier access to information. So these are typical applications of urban planning. Now, in urban planning, we can use the GIS at the different levels for different sectors, okay, at the different scales. Like you can say the different functions, scale, sectors, stages of urban planning, where we can use the GIS are like different scale. We can do the analysis at a whole. You see, your database same, and we can do the lot of analysis on a whole. You can say city level, ward level, on a zone level. So all those things we can do. Means your planning scale can be anything, and the same database can be used at the different scale. So that is. There's one question: how can number of trips and mode of transportation used in GIS? You see, in GIS, when we have the transportation network on digital domain, okay, like what is the road, what is the traffic on road, where are the intersections, what is the timings of intersections, battis, okay, traffic density, what are the other connections. So all these informations simultaneously can be used, okay, with respect to time to decide about the transportation links. That suppose, for example, like if we want to move, say, from one point to other point, so what is the shortest route? Now, shortest route in terms of distance, shortest route in terms of time of traveling through the different modes, like what the Google is doing. Simply when on a Google, you just put like you want to go from this place to this place. This gives you alternate ideas. Okay, like this is the route and this is another route, or this is another route. So all this thing is in the backbone, GIS is working. Okay, all aspects, like at that point of time, okay, what is the traffic on the different stretches of road, how many number of red battis are there, what is the distance, what is the road width. So many more these informations are basically integrated, and then decisions are made to determine the transportation mode and the alignments. So that is that can be done in real time in GIS. So that was the question from NR Gauri. Okay, so any other question, please feel free to even ask, or you can just put your question on chat box. We can discuss it. So in urban planning, at the different scales we can do. You see, the same database, as I said, that it is scale independent. Your digital data is scale. There is no scale of digital data. That we can use the same data at the different scales. Like you can do the analysis for a whole city scale, on a ward basis, on region basis. Okay, you can do at any level. Like you can determine the say if you want to determine the literacy rate, what is ward-wide literacy rate, what is road density in a particular ward. So all those things you can do very, like doing the overlay, digital overlay in GIS, and by putting the locational based, you can say data mining from the database, we can determine that, okay, what is the number of road lengths in a particular ward. So you can determine the road density. Later on, the same thing can be used to determine the transportation, whether your circulation spaces are adequate or not. So those things easily you can determine on ward basis, on a region basis, on a zone basis, or city basis. Okay, and similarly, you can do with respect to other type of cities. Like same sort of examples we can use in zonal planning or in locating facilities or facility provisions. So that can be done at any scale. Then the most frequently involved sectors where we can use the GIS in urban planning are land use, like land use zoning, like permitting the land uses, identifying whether a particular type of land is feasible or not, correlating the partial information with the surrounding other type of, you can say, infrastructure things like roads, road widths, electricity lines, power lines, many more things you can correlate, and you can decide about the land uses. Transport planning, of course, depending upon the population density, availability of land, connections, missing links, a lot of other things you can use simultaneously to decide about the road and circulation spaces. We can use a lot of GIS in housing, deciding housing, type of housing, land development, and of course, in environmental monitoring and protection, we can use GIS, like sorts of UHI, assessment of urban heat islands, locating the you can say water bodies, or developing the green spaces within the cities to target sort of environmental aspects. So that we can do in GIS. And at each scale, urban planning, there are different stages. Okay, means on each scale, we can use the GIS while doing the urban planning at the different stages, like determination of planning objectives, like helping us in better identifying the objectives while we are planning a city, analysis of existing situation, modeling and projections, like determining what is, like for example, like facility gaps, like identifying facility gaps on a ward basis, public facility gaps in ward basis, zone basis, so that you can determine the existing situation, circulation spaces. Okay, land use, type of land use, densities, whether your land use or like zonations or restrictions are peoples are following it or not. So all those things, you can existing situations, you can model the existing situations, even we can predict it for future development of planning options, scenario generation, selection of planning options, plan implementation, monitoring, plan evaluation, monitoring, feedback mechanism. So in all these aspects also, we can use GIS and GIS databases. Okay, so typical functions of GIS for urban planning are like basically from the database, like we need to capture the data using remote sensing and other sources, basically spatial, non-spatial data, that is GIS database creation. And from the GIS, we can do the spatial query and mapping. We can do a lot of processing for urban planning. The spatial analysis and data modeling can be done. Data mining can be done. Data analytics can be used, okay, for planning objectives. And in the different sectors where we nowadays, if you look at the industry standards in our country, we are at the beginning stage, but in developed countries, GIS is very much used. Like if you look at the data for a general administration, okay, where we can use the database management related applications are used. Almost all general administration purposes related to urban planning. Okay, then mapping related solutions, spatial analysis. So look at it, spatial analysis less, spatial modeling is also very less. So general database management system making queries, that is mostly used in case of like plan making, development control, general administration. Okay, so these are the different extent in which we are using these GIS related services. Like the more routine general administration and development control works, like enforcing building bylaws, identifying, monitoring the building bylaws implementation in the cities, that or monitoring land use, you can say things. We can development control works. Okay, these are the planning, urban planning related applications. And for these two type of, you can say, works, we can use a GIS. Like in first case, database management system, management of records, land use records. Like if you have GIS database of existing land use of cities, where you have the building footprints, you have roads, you have water supply lines, power lines. So you have digital records. And tomorrow, if while doing planning or monitoring, you need some information, you can very quickly, you can extract from the records. So GIS is basically using very robust professional database management systems, where we can keep our records and we can use the GIS. Thematic mapping, creating GIS database themes, while so that these themes can be overlaid for making decisions. So thematic mapping, we are using it for general administration, development control works, land use management, building control application processing, like issuing basically land pattas, or you can say converting land uses. Here also we use this information databases. Land availability, land development monitoring, industrial, commercial, retail, fraud spacing, recreational, countryside facility planning, facility management, selection of public facilities. So land use, transport, strategic planning. So these are the categories of general administrative works and development control works where we can use the GIS. So basically, planning at different scale requires different data and techniques. Like raster data are more useful. Raster data means cell-based data. So generally, we use both data, vector as well as raster. So for continuous surfaces like topographic elevation, land use, land cover, soil, such databases which are continuous in nature, raster data sets are more useful. Okay, like satellite images, they are in the raster. But like the discrete objects, like say facilities, buildings, roads, pipelines, they can be vector data can be used to create digital databases for or discrete objects. Okay, and in GIS, land use transportation related, we do the lot of land development and environmental sector, and key examples are like site selection, land suitability analysis. This is another area where we can determine the land suitability for the different land uses. So tomorrow one can, while planning, doing a master planning, one can decide the land use of one particular parcel of land. So even you can target the sustainability of resources. You can put the which type of land use at what place as a function of natural resources. So that sort of planning can be done very easily in GIS. Network analysis, route selection are the most frequent used transport in the transport planning that you can do very easily in GIS. Nowadays, ready-made algorithms are available in GIS softwares like in ArcGIS. Network analysis module is available where we can analyze the different sort of networks. Like you can network of water supply lines, sewerage systems, road networks, railway line. So those sort of network related, you can say, applications can be sold. Even like you can generate the cost maps, or like cost means not traveling cost, time cost in terms of costing. Okay, we can select different sort of alignments of roads, pipelines, and many more. So a lot of analysis are available. One can just have a look on ArcGIS, and there are a lot of tools are available. Even if you people are interested, I can show you the different tools. So like in this is GIS, ArcGIS tool, and just look at it. These are the different analysis tools, and this network analysis tools are there. So here we can analyze the lot of tools are available where we can analyze the different sort of route planning and related things. So variety of tools, hundreds of tools are available for each aspect, and which are very useful in urban planning related applications. Okay, so urban environment planning management using buffers and overlay processing. Like you see, buffer is sometimes in urban areas, doing urban planning, certain areas they need to be protected. Okay, so while doing automatic planning, you can just put buffers on those areas so that your planning decisions will not be implemented in the buffer areas. So sometimes you can force your analysis to keep certain facilities in particular stretch of land, or sometimes you can avoid, or sometimes you can include. So that thing can be do through the buffers. And while in making decisions or in scenario analysis, when your facility selections or a decision is governed by a number of information themes, then you can overlay the different thematic, you can say, layers, and then you can do your analysis. Like in ArcGIS, okay, you can have those things like in analysis tools. Here in analysis tools, you can, like in here, this analysis tools, here in the proximity, you can find the buffer. So this is buffer, you can create different type of buffer, point, distance, polygon, or even you can create buffer along point, line, polygons. You can do the overlays. Okay, even you can extract the different information. So a lot of tools are, all sorts of tools are available where we can use GIS for the urban planning related applications. Okay, okay, so these are typical like how we can use GIS. So in the GIS helps us in integrating the remote sensing capture data, other databases from that is captured from hard copy maps or some other sources. And these are the like GIS is can be used for all sorts of applications like resource inventory, creating database, analysis of existing situation, modeling, projection, development of planning options, selection of planning options, planning, implementation, and their monitoring. All these things can be done in GIS. Of course, remote sensing can help us in data capturing like this resource inventory and monitoring and evaluation of plans. Other type of data, other models in integration with the GIS can be used for all sort of applications. Okay, so like application resource inventory, your GIS Other data capturing technologies like UAVs, means drones, lidar, terrestrial scanners, GPRs, they can be used to capture the different type of services, a different type of objects, subsurface, and on the surface, what are the different objects, what are the locations of different type of facilities, okay, infrastructure facilities. All these things can be captured from remote sensing related technologies, and that same database can be stored in GIS. Even satellite-based positioning solutions nowadays, we can use to capture the data. So in X, Y, and Z, and directly in the field, you can do the mapping. So using GNSS, earlier we used to know about it, GPS. So GPS is a type of GNSS system. So using GNSS, you can create maps directly from the field. Like just take a, like you are moving along the, say, roads, so you can create a road map. So all sort of data capturing, resource inventory. Suppose we want to identify where are the schools in a city. So simply you visit this, capture the location of schools in the city, just go there and just capture the coordinate and then transfer into GIS, and you can have a digital location map of schools. Similarly, from other sources also, like from the Google or some open sources nowadays, through the cloud sourcing, we can capture such information, and that can be stored in GIS databases. Mind it, and their characteristics also can be attached, because we are storing the location and the characteristics are associated with the location. So resource inventory is very good in GIS. Then another major application is analysis of existing situation. Like we have the whole urban information or a city information into different thematic layers. So with respect to any criteria, any variable, any problem, you can analyze by overlaying the data set. Okay, you can determine the existing situation. Like I can give the example of it, like determining facility gaps. Okay, determining missing links of roads. So that you can do, whether your roads are adequate in a city or not, whether schools are adequate in different areas or not, whether fire stations are adequate or not, so whether petrol pumps. So all such things we can to existing. So GIS can help us to store, manipulate, analyze physical, social, and economic data of a city. Planners can use these data sets to make special queries and to determine the existing situations, current situations. And through the map overlays, we can determine the overlaps or conflicts between land development and environment, and land development with other type of services. And areas of environmental sensitivity can be determined very easily through the overlay analysis. So that is sort of existing situation we can analyze in GIS. Then GIS and remote sensing both can be done for a lot of modeling and projection studies, like basically determining future growth, like in which direction the urban area will be increasing. Okay, so like urban growth analysis, like urban sprawl, in which direction it is extending, and then same can be modeled to predict it in future. Like we can predict land use, land cover changes, we can predict urban growth, and such predictions helps us in making appropriate provisions for public services in your master plans. And you can allocate, you can locate the, you can say allocate the land for future services. If you have an idea that in which direction your cities will grow, how much it will grow, and what will be the extent of urban areas in the future date. So all those things can be very easily done in through the modeling things in GIS. And GIS can be used to model different development scenarios. You can do the for example, you can simulate the urban growth by considering the different scenarios of transportation network. Suppose tomorrow you are putting one more highway, then how it will affect your development. If you are putting a certain industry, so industry will lead to the lot of, you can say, employment generation, a lot of migration. So how it will affect the development. The other type of services, how they will affect and govern their development. So all those things, scenarios you can generate and you can analyze in the GIS through the modeling. Okay, so corresponding to different land use policies, we can develop the land use patterns, land use scenarios. Okay, then also the spatial modeling and spatial distribution make it possible to use the impacts of existing trend of population, economics, and environmental changes. So a lot of these things we can do in GIS because we have the digital database, and database is attached with location, and with respect to location, multiple themes or informations can be integrated, and by just looking across the data sets at a given location, we can determine the adjacent situations, and we can fit mathematical models to predict them for future. So all these things can be done very easily in GIS. Okay, so in development of planning options, as I said, that we can generate corresponding to different policies, we can generate different land use policies or urban growth scenarios or land use plans. Then out of number of options, which one is the optimum? So corresponding certain criteria, you can compare your planning options, and then you can select one optimum sort of thing that can be done in GIS only. Very accurately you can do it in GIS because you need to integrate multiple sort of informations. You look through all the options simultaneously, and then you need to use the power of computer to evaluate the different scenarios. That can be done in GIS only because all the information data they are stored in database management systems, and we can access the data, we can mine the data, we can use the big data analytics, okay, to analyze the data sets corresponding to location or corresponding to characteristics of the locations. Then plan implementation, we can just like monitoring the land uses, monitoring the building bylaws, whether they are followed in development at a certain place or not, like locating the infrastructure facilities, whether they are implemented as per the plans or not. So all those things can be very easily compared with respect to time from the repetitive coverage capturing of special data about the cities. Then you can just compare them, that how changes are taking place, whether desired changes are taking place or not. So such things you can do very easily in GIS. Then for urban planning, your plan evaluation, monitoring, and feedback, okay, whether how much your plan was beneficial or not. Just I given in the last lecture, I was presenting a case study of monitoring of like watershed development, what impacts watershed development have. So those temporal changes you can compare. Always you can do in GIS. Like the same can be done in case of urban areas as well. Like you can use the remote sensing GIS to help them monitoring the environment. You can use the land use changes. You can monitor the building bylaws. You can see that how the development is taking place as per the plan, it is taking place or not, unauthorized construction. Okay, even you can use for property taxing as well, because you have the database, you have there all the areas about information about the properties and built up areas, you can tax it. So those things, and in all these operations, mind it, there is no personal biasness. You are doing all these operations and analysis without any personal biasness. There is no, you can say, ambiguity. There is no chances of corruption if you are using GIS in doing the objective decisions. Okay. So this was the urban planning. Like I'm just so these are the biggest scope or the potential of applications of remote sensing GIS in different aspects of urban planning. So if you have any questions, okay, you are welcome. We can discuss it. Any questions, please, for whatever we discussed so far. Even if you have any queries that how I said many things, like how one particular thing can be done in GIS, even I can show you in the GIS software where you can do it. So please feel free to ask the questions and we can discuss them. Like on chat box, I have a question. It will be good that you please unmute and you can ask the questions. You introduce yourself and ask your question. It will be good that we can talk. So one question on chat box. Yeah, please.
It's Pooja, sir.
Yeah.
I'm research scholar from DCRUST only.
Yeah.
So my research area is on green spaces. So I just want to know, can we separate public green spaces and private green spaces through satellite imageries?
Definitely.
And how can we calculate? Yes, sir.
Yeah, you can do it.
And how can we calculate cooling interaction between nearby green spaces, sir?
You see, that's why I said that you can determine through the energy balance modeling or through the Earth surface temperature. Like you can calculate Earth surface temperature using thermal infrared data, satellite data, and so Earth surface temperature, and then you can relate that Earth surface temperature on a cell basis with their green spaces. So that was, so means you can correlate the basically green spaces and how it is affecting your macroclimate in terms of land surface temperature. Okay, first thing. Then your second question was that you can separate the green spaces with the rest of things from the data sets. Definitely, public and private. You see, always in the GIS, we are using the different sort of, you can say, decision things. Just like I will be showing you a case study where we have captured the buildings, different sort of building, like what are the institutional building, what are the basically residential buildings. So in the similar way, we can separate by using the appropriate decision, you can say, criteria to separate the green spaces in public domain and in private domain. Okay, like shape of land use parcels. Okay, association means association of those parcels with the nearby areas. Okay, association with the roads, shadows. So these are the texture. Okay, so these are the aspects which we can based on which we can definitely we can separate the private and public spaces from remote sensing images.
Thank you, sir.
Any other question, please?
I request participants, please, if there is any question, you can ask or drop in a chat box.
Yeah, I'll be happy because you see, the queries like application queries means I'm saying many things. I just mentioned a lot of things that we can do this and this and this. So if you have any queries, please let me know how actually we can do it, so that I can.
There are two new questions. So there are two new questions in the yeah.
In chat box, sir, there is a question. Can we implement deep learning in ArcGIS?
Yeah, deep learning, nothing but the data mining and basically data analytics. And the whole GIS is nothing but the data analytics only. Always we can integrate deep learning, ANN, any machine learning algorithms with the GIS. And on top of it, always we can use it. How many years of data required as an input for forecasting purpose in UTP? You see, basically forecasting. You see, we in the all type of modeling and forecasting works, we are using some data sets. So what type of algorithm we are using forecasting and what is the minimum data set required for that algorithm, that has to be done. Like in the yesterday probably Dr. Ankita have discussed urban growth modeling. So like how many number of historical input data sets one can require to predict it for future. So that is the case-to-case basis, but definitely if you have more data set, your predictions, your modeling things will be more accurate. But modeling cannot be done from one or two data sets.
Sir, there is one more question. Is there any tool in ArcGIS which can be used to predict groundwater levels based upon previous year's database?
You see, there's a, yes, in ArcGIS, there's a, we can create a groundwater inventory in digital domain, just like we have basically piezometer wells. So piezometer wells, their coordinates will be a point map in ArcGIS or in GIS. Then their fluctuations, water level fluctuations in different time periods, that information can be attached, attribute information with the data sets. Okay, and for future, like if you provide the, like how groundwater level will change, it will change if because of variation in two variables. One is recharge and withdrawal. So if you have the meteorological data, of course you on a cell basis you can determine the recharge, how much recharge will take place. Okay, that can be done very easily, very simply, with using the simple methods. Okay, and if you have a withdrawal data, then you can predict the change in groundwater elevations as well. Look, I am just simply giving an example. Like if you have the aquifer extent, okay, if you have the aquifer extent, like if I have a groundwater well locations, and if I have their lithologs are giving me the information about the soil formation as a different depths. So from those lithologs, if they are available for the different points in your area, I can generate a boundary of aquifer, okay, using the interpolation of those lithologs. Then it means that that information gives me the depth of aquifer at the different locations, okay, depth of aquifer at the different locations. And based on the pumping test that is always done for piezometry wells. So if you have that data, based on that, there's a one property of aquifer that is called a specific yield. So if you have a specific yield, then based on change in fluctuation, like how water has changed between two time periods, like, okay, if rainfall is more, withdrawal is less, then recharge will take place, so your water will rise. So change in water level between two different time periods, if I know that fluctuation, I simply multiply with the specific yield, okay, that gives me the volume of change in your water inside that aquifer. So I can determine the perfectly recharge and withdrawal very accurately on a cell basis in GIS. If somebody is interested, we can discuss it separately in detail, or you can write to mail me. I can share you some paper and case study about it, that how it can be done. But it is very easily, very accurately you can do it. If you have provided, if you have some data about the like groundwater.
Hello.
Yeah, please go ahead.
My name is Sachin Velekar and I'm from Goa University. I'm a postgraduate student from computer science and I have a question to ask.
Yeah, please.
Yes, sir. You know, like because of the distances the signal have to travel from the satellite signals,
Yeah.
and all the potential obstacles in between. So
Yeah.
satellite data provides, you know, very low satellite bandwidth at this point. So most of the time, you know, where there are trees and all the very dense forest regions, where you know, so don't you think satellite latency can be a significant problem, wherein the signal can't reach properly because of the some of the obstacles like canopies of the tree? So how is the satellite able to capture data at the point, means like location data at a point wherein, you know, there is an issue with the signal latency at these particular points?
You see, very right, very good question. You see, always basically remote sensing data is not captured in all wavelengths. Mind it, because all these aspects, what you are flagging, all they are investigated in advance, like which are the wavelength regions, wavelength bands in which sufficient amount of electromagnetic radiations they are reaching on the surface. Your atmosphere is also interfering with those radiations, electromagnetic radiations. Like your radiations can be scattered, they can be basically absorbed by the gases and aerosols and gases, different type of gases, water molecules. Then remaining, so mind it, we are just like you can say the radiations in UV range. So radiation of ultraviolet range, they are not coming on the ground because all is absorbed by the ozone. So similarly, the different gases and different aerosols, different type of particles, different type of substances, they interact with the atmosphere radiations. And we have information knowledge, and always we try to design our sensors in those ways to capture the data in those wavelengths where your atmosphere is particularly transmissive. It is not, you can say, changing the signatures, or it is not changing the energy. Another factor is that we try to, even if some amount of energy is absorbed, okay, even we try to operate our sensors in those wavelength bands where we have highest energy from the sun in passive mode. And in some cases, when we don't have like sun as a source of energy, we use active remote sensing instruments where we use the basically our own source of energy, and in infinite wavelength bands, okay, we basically emit radiations, and then allowed that those radiations are allowed to interact on the surface matter, okay, and then after the interaction, the amount of radiation that is going up in the atmosphere, we are capturing those radiations. And primary objective of remote sensing is to capture the biophysical information, like plant canopy. there are many applications where we need plant related information. We need the plant health, we need plant coverage, we need how much chlorophyll that is available in the plant leaves. So for those things, we target those wavelength bands which are interacting in a better way with the plants, like near infrared band, near infrared wavelength. So in the near infrared wavelength, we get highest reflectance from the vegetative parts. Okay, so primarily those wavelengths, they are used for those things. There are certain wavelength bands where we don't have any reflectance from vegetation. Okay, so depending, that's why we operate all remote sensing instruments in multiple wavelength bands. Like in hyperspectral remote sensing instruments, they operate in more than 200 bands. Okay, like Hyperion, it operates in 224 bands. Iris, it operates in 240 bands. Okay, so what is our application, target application? How the atmosphere is interacting with the radiations, which are the wavelength regions in which it is transmissive, what type of interaction, what type of biophysical variable we are targeting on the ground. Based on these criteria, we try to select wavelength bands in which we should capture the data sets.
Thank you, sir.
Any other question, please? Okay, no questions. So as far as I was talking about the planning, so basically, you see, GIS is nothing but a sort of data mining tool. It is using very heavily big data analytics. You see, you can do any type of statistical analysis. You can fit any type of models. You can do the predictive modeling. You can do the scenario analysis. You can extract a type of information in a particular, satisfying a particular condition. So all these are nothing but a big data analytics tools. Okay, and all information, it is stored in professional database management systems, which are where data is very secure. You can access data very fast, very accurately. So that's why all type of like deep learning sort of thing and all, they can be very easily implemented in GIS along with the GIS. Any other question, please? I hope like you can go to do the scenario modeling. GIS is the best suited for scenario modeling sort of applications, because it gives you capability to overlay the database based on location, and then you can put a lot of conditions. Okay, a lot of decision, you can say criteria to investigate your outputs. And it also facilitates concurrent use, like same database can be used by the multiple users, which is otherwise not possible by any other means. So that's why it is very useful, and its main power is not mapping, its main power is data analytics. That you can do the lot of analysis using data set, you can use a lot of mathematics and logics to arrive at solutions. Okay, so if you have any questions, please, again, you can ask or write on chat box, or I can move ahead with a few case studies. Like one is remote sensing for urban planning. I'm just putting a case study. So I'm just giving a glimpse. Like you can, for urban areas, to know about the temporal changes in how the city is growing, how in which direction it is growing. Always simply using remote sensing and image processing, you can determine that how it is moving, in which direction growth is taking place. Even not only the built up areas, you can track the vegetation, how the forest cover or vegetation cover is changing with respect to time. Always you can do it. Okay, so that is then you can do basically land use land cover change. You can estimate temporal, analyze the temporal images, you can analyze them. Okay, then you can prepare land use, and you can track how the things are changing with respect to time. Then another very important application is you can correlate urban growth and environment, just like how the urban growth environment like vegetation, you can say vegetation, or you can say your urban heatlands, temperature, green spaces, that one question was that how you can relate with the green spaces with the you can say environment. Of course, you land use like UHIs, you can correlate, you can overlay, then you can establish relationship based on the time. So you can extract UHIs from the satellite images. Okay, so this is the flow chart, how you can obtain the UHIs. Okay, we can obtain the AOP transpiration green spaces. So simply, sometimes green spaces also, like if you have the like ET, so even from the AOP transpiration also, you can have an idea about type of green spaces, density of green spaces. And wherever your ET is more, it means you have the more green spaces. So those things can be done very easily, or indirectly using many variables also you can correlate with them. So like this is the example where urban growth is correlated with the land surface temperature. So you can have an idea about like wherever you have the more built up surfaces, your land surface temperature is more, okay, due to the basically sensible heat. Because this is a perfect energy balance. You see, on the land, when the energy is incidented, it is interacted in three ways. Either incoming solar radiations, that is net radiation, it is partitioned into three parts. One part radiation is used in latent heat. So if you have sufficient moisture and vegetation, the significant portion of incoming solar radiation, it will be consumed in latent heat. It means in evaporation and evapotranspiration. And one part is absorbed by the ground, okay, that is ground flux, and the remaining portion, so net radiation minus latent heat minus your ground flux, that is available sensible heat. And so that sensible heat is primarily basically flux exchange between your land surface and atmosphere. So the sensible heat will responsible for increase in basically your temperature, air temperature. So if your ground flux is less, okay, like if you have more hard surfaces, reflective surfaces, then your ground absorption will be less, and more you can say radiation will be reflected back. Similarly, if you have less vegetation, your latent heat will be less, and your amount of radiation there, it is getting converted to sensible heat. So sensible heat will basically reflect into increase in air temperature. So perfectly, your surface energy balance can be related with land use land cover things very accurately, and that is on a cell basis in GIS. That is the example where how we can relate with urban growth or change in land use land cover with the different type of environmental phenomena. So this is the one example that how we can correlate the basically land use land cover and LST or land use land cover or built up density, and then you can have perfect correlations you can study, and how it will changing with us through time. Even such things can be used to for adaptations. Okay, like you can decide the land use based adaptations, like you can create the green spaces, you can create artificial water bodies, so they will change the energy balance, and you can contain the effect of UHIs in your areas, because UHIs in urban areas, they are basically sparingly effect. If you convert the land use land cover, less green spaces, less water bodies, more sensible heat, okay, and your surface will be heated, land surface temperature will be more, you require more cooling, so you will use the ACs and many more things that will again lead to the CFC gases, and so it is a sparingly effect. So a lot of, you can say nowadays emphasis is going on, a lot of research is going on, that how basically we can identify land use land cover based adaptation and mitigation measures to deal with the USIs and the climate effects in urban areas, because that is very severe in urban areas. We did a lot of studies in this area, and we find out an alarming sort of situation in urban areas, because uncontrolled conversion of previous areas into impervious one, they are leading to the very unhealthy, you can say, or unsustainable environmental conditions. Okay, like this is how the urban density of built up density is related with the UHI. And see, it is perfectly your LST curve and built up density, land density is their trend is perfectly matching. So it is indicating that wherever the built up density is more, okay, more temperature will be, land surface temperature will be more, and this can create a USI effect. Then this is another case study where I was telling that one of my PhD student did a PhD research where we developed some algorithms by which we can automatically extract the building footprint from the satellite images. Okay, and different type of you can say footprints, like industries, industrial buildings, institutional buildings, slums, even plant buildings, plant areas, all those things can be extracted automatically. And we have used certain contextual information, certain you can say geometrical information that is inherently available in the remote sensing images, okay, to develop algorithms to capture those features automatically. Okay, so again, our study was Jaipur city only, and we use a high resolution data sets, QuickBird, okay, that was 24 meter in multispectral mode and 0.6 meter in panchromatic mode. And we had basically tried different sort of, you can say, methods and algorithms to extract the building footprint, different type of building footprints, like building extraction based on the threshold values, like you see, type of reflectance, amount of reflectance that is available on remote sensing images, the brightness values and numbers which are visible on you can say on remote sensing images. So that reflectance is a function of physiochemical characteristics of object and surfaces in our surface. So two surfaces are different by any means, by the chemically, physically, or surface characteristics wise, okay, your reflectance bound to be different, and those differences can be captured, that can be used with some ancillary information to separate them. So that was the first building extraction based on threshold value that we identified the for different sort of buildings, threshold values and brightness values, and then we captured it. Okay, so there is a question. No questions. Okay. The second method is building extraction based on the texture. You see, texture is available inherently. So depending upon the different type of brightness and different sort of chemical characteristics, your color combinations, variation, spatial variations or frequency is different. That is defined by the texture. So by capturing the texture, and we know the texture of residential buildings is quite different than institutional buildings, commercial buildings. So those textural differences and their association with respect to different type of land uses, they are basically used in developing the algorithms to detect the building footprint. Then we used the building shadows and the corner information, like shape of different, like a road is also, concrete road is a built up surface, and rooftop is a building surface. But how they can be separated? They can be separated, we are separated using the shape of the objects. So those objects are captured, their shapes are quantified, then they are compared, and those comparisons are based on the built up knowledge base, and using those big data analytics, we can compare that with the knowledge base, and then we identified that, okay, this sort of feature it might be this. So automatically those decision rules are implemented to identify those things. Then another algorithm we tried to extract the buildings based on threshold, texture, and shadow. Combined, all these three are combined together, and I'm showing the results of all those three. Okay, like this is through the threshold that we have the remote sensing images. Then basically we have separated the non-building part from the images, like vegetation through NDVI shadows. So detect the vegetation shadows. Then we have put a mask on the buildings so that a decision rule says they should not be overlapped with the decision of vegetation. Okay, then we did a post-processing rough building mask. We have apply a morphological filter, okay, targeting this different sort of shapes, and then identifying the filling holes like a building. So in some building parts, some patch is having some reflectance, but that is a part of building. So such patches are filled through the filtering techniques, and then basically final buildings are extracted. So this is the case study. Then there's the second methodology based on the texture. Again, so the texture, remote sensing images are taken, the textures are quantified, images are segmented, and after the segmentation, the textures are quantified. Then we use the k-mean clustering algorithm for generating the building mass. Okay, and those building, you can say mass and using the texture generated pixel values. And then in post-processing, we have separated, classified those, you can say texture pixels into different building classes. Then we have combined with the building shadow and corner information. So this is the methodology that how we compared the corners, the shape of the different buildings, and we use the shadows. Like if you have a multi-story building, okay, it will have a shadow in a one particular direction. So those shadows are identified through the ratioing techniques, and then those objects are, so shadows are quantified, and then based on the shape, we have tried to identify different type of the buildings. And in another method, we have combined together all these three: threshold, texture, shadow, and shape. And then we have obtained basically the building parts. So now just look at it. These are the building footprints, okay, that is obtained from the remote sensing images. Like in the background, there's a remote sensing image, and how this magenta color is a layer that is automatically extracted from the buildings, using only basically different buildings and different methods, like the first ABC part, A1, B1, C1. These are the images and digitized images. Then A2, A3, B3. These are the classified outputs, and then A4. These are the extracted from the threshold values. These are from the automatically from the threshold algorithm, and then these are 5. These are using for the texture, and these are used for the texture, shadow, and threshold. So just look at it. Automatically, the combination method is so accurate that it is completely capturing the data sets. So these are the commercial buildings and educational buildings. So we have selected automatically, and so based on the rule set, okay, we can capture and we can automatically extract. Now, mind it, this is so useful when you are analyzing the whole city. So while your algorithm is ready, you can process and you can now extract the different type of buildings. Such an information can be very helpful in building tax and tax in property taxing and many more sort of applications, like in planning or renewable energy, solar panel placement, and many more studies. Such an information can be used. This is extraction of plant buildings. Now look at it. This is perfectly capturing, because plant buildings have perfectly particular shape. They have their shape can be defined in terms of ratio of their width and length. And see this part where we are used basically combine together the texture, shadow, and shape, and basically thresholds. And your outputs are so accurate, seems to be so accurate that automatically we can capture them. These are unplanned buildings, like unplanned colonies, but still our algorithm is working fine. That at least building tops and the building plans areas, they are well captured from the unplanned buildings as well. And that algorithm where we combine together, that has performed in a good way as compared to other one. These are the industrial buildings. Okay, we have taken the example of some industrial buildings like shades, petroleum, these things, and satisfactorily algorithm is capturing the industrial buildings as well. So mind it, in the same building, same sort of image, we can implement different sort of logic. So all the logics simultaneously, a rule set for industrial building, a rule set for institutional building, for residential building, plan, unplanned, those sort of classification can be done through using a programming on the top of the image processing software, and we can extract the different type of land use classes, different sort of buildings simultaneously. And these are the slums. Mind it, through the slums, because there is no separate pattern or you can say pattern of road or shape is valid, but still with a good accuracy, we are able to capture the slums as well. This is actual slums nearby MNIT in the Jhalana area. So their images and their their top part, footprint, except you can say they're captured. Of course, in the slums, we are not able to capture the individual buildings because they are so connected, so that it is difficult. But patches of buildings, they are able to capture automatically from the satellite images. Now mind it that in this output, nothing is coming out. No road is coming, nor vegetation, other type of built up surfaces like parking lots, they are not coming up. Only building footprint is coming up. Okay, so that was the case study of you can say where using data analytics techniques, data mining, and big data analytics techniques, how we can process the different type of contextual and biophysical information that is available in remote sensing images to capture the built up part of the areas. Any questions, please, from this? If you have any questions, you are welcome. So there's one question on the toolbox. So this is, can you give ideas about satellite image compression using deep learning? You see, image compression, yes, definitely. There are variety of, still people are using different sort of image compression techniques. You see, image is what? It's a rectangle array of pixels. Rectangle array of pixels. And compression of satellite images, essentially you need to reduce the number of data points without compromising your information content. That is the soul behind this data compression techniques. So generally, sometimes if you know something, you can cluster the image into different segments, and then you can target similar sort of clusters can be converted into single databases. Okay, so it means inherently using deep learning, we can identify the different hidden patterns from the pixel values. Then we can combine together into objects, and through that multiple pixels data points, they can be converted into a single object, okay, without compromising the inherent conditions. So that sort of techniques can be used for data compression. And of course, that is through the deep learning, other machine learning techniques can be used for such things. I hope I have given some hint that how we can use it for data compression of satellite images. Any other question, please? Okay, there's another question. Is it possible to identify the damages in buildings using RS sensing images? Of course, you can identify damages. What type of damages? If you are thinking of earthquake sort of damages, yes, you can do. Okay, but if you are saying that there are small cracks in the buildings, such small things cannot be identified, but big damages, you can capture it from high resolution satellite images. Like damages due to natural disasters, floods or earthquake or sort of things, you can always, you can map them. You can, I can, for your information, I can let you know that presently we are doing one big project for Ministry of Home Affairs, Government of India, and we are doing, basically we are developing disaster risk index for 60 Indian cities. And that information is Government of India is going to use, like Government of India has created a mitigation fund. They want to rehabilitate, they want to basically reduce the chances of, you can say, hazards in cities, and they want to identify those areas where vulnerability is more due to natural disasters. So we are developing that disaster risk, and we are using extensively remote sensing images, okay, to we are segmenting, means to identify the different sort of built forms. Okay, we are using the satellite images. We are clustering, we are dividing the city into different clusters based on proxy variables of built forms into clusters of similar sort of building topologies. And then those areas topologies, we are determining the risk for different type of earthquakes and different other disasters. And then ultimately we'll developing an index that gives us an idea about relative risk of disasters on a cell basis, so that we can prioritize the different parts of cities for mitigation and adaptation works. Okay, so that can be done through the basically a lot of, you can say, knowledge base and data analytics can be used in images to identify the hidden patterns and things. Any other question, please?
So there was a question in the chat box that before compression, classification is necessary or not?
No, not necessary. Not necessary. Because you see, we can compress the images as a function of reflectance. For example, as a function of pattern in reflectance or a texture, means you can use any type of inherent characteristics that is available. Of course, sometimes even we can refine our classification through these compression techniques, like object-based classification techniques, where we reduce the decision points. Like on per pixel classification, you are making decision of classification about 1 pixel. But if you segment the whole image in homogeneous clusters of brightness values, okay, and then you can apply your classification decisions on those reduced number of data points. So that is example where we can refine the even classification also.
Sir, but at the time of compression, don't we lose certain type of informations? Let's say digital number, the clubbing of different clusters, these pixels. Don't we lose that information?
Yeah. If our clusters are not homogeneous, then we lose it. Just like, for example, if you are targeting the clusters of built-up part and vegetation part, you want to separate them. So by clubbing the different sort of buildings in a one group is okay. That is not losing any information. Like clubbing the different type of vegetation areas in a one group, that is not affecting our application. So even nowadays, using very like hyperspectral data sets, even we can do the clustering for a very subclass level also, like vegetations. In vegetation, we can do the clustering for different crops, different type of forest, different type of even vegetations. Okay, so what is our target and what is type of data in our hand, we can sometimes preserve it.
Thank you, sir. Thank you.
Okay, so there is another question. Okay, no,
there it was. Thank you from the participant.
Okay, it's fine. It's fine. So I think we are approaching towards our time. So I'm. This is one other case study of a sprawl. So yesterday Ankita might have covered some portion of it. So I'm not, because time is less. I'm showing you the zonal development plan that we are preparing for one city's certain outputs and how we did in GIS. If somebody is interested, please feel free to discuss it some other time as well. So I'm just skipping this. Yeah, land suitability also we did it for 2 cities. So yeah, so I'm just for the city in Sujangarh. Okay, in Rajasthan, we just developed, just like we are completing this work. So we are developing basically zonal development plan for and how we have progressed, what type of data we used. Okay, so I'm just going through it. If in detail, we have short time. So if somebody is interested, we can discuss it in questions. So these are the different stages of zonal development planning. Like the first stage is capturing the existing situation, what is there presently. So that is the first part, preparation of detailed base map. So the base map that includes details about everything. Okay, where are the circulation spaces, where are the roads, where is the railway lines, where are the other type of services. Okay, where are other different type of administrative boundaries. Okay, different water bodies. So all that is base map. Okay, so we have we use the basically data. Of course, we use the different type of data, satellite images, drone images, and the cadastral revenue records. We use other type of maps which are available. We have basically georeference them and convert it into GIS databases. And then finally, integration of a lot of information from the different sources, we have prepared the base map. Then the second stage is basically preparation of detailed property level zonal based map within the municipal limits of town. Like what are the individual partials, the partial boundaries. So the partial boundaries, they are basically captured from ultra high resolution drone images. They are having the resolution of 10 centimeter. So from those 10 centimeter drone images, we capture the partial level details, that is means property level details. Then we have created a digital database, different layers like layers of routes, railway lines, property lines, khasra maps, digital khasra maps, then electrical lines, all type of facilities. So their database was created. Okay, so that was the first part, data capturing part, and then converting data part into digital one. Then in the second stage, superimposition of all commitments, revenue maps, government land, natural major physical features, ward boundary, and base map. So superimposition, because you see, all information is created with a common coordinate and precision system. So all the characteristics of different locations, whether it is a partial, what type of land, what is khasra there, whether electric line is there or not, this ward mein, which ward it is, which zone it is, which boundary it is. So all data set is in digital domain. So superimposition is nothing but overlay of different themes. So it is very easy. Simply you open the files in GIS and you can generate the outputs. The superimposition is very easy. This commitments is nothing but already commitments made by the municipalities, like they have given some land use rights to the users. So their maps were there, they are georeferenced, they are scanned, they're georeferenced, and they were transferred into digital domain, so that we know that which portion of partials and lands they are committed already for which type of land uses. So those need to be honored in their while planning the development plans. Okay, so that was done, and simply government lands, we are captured the government lands from the revenue records, and all those things, because data is digital in the digital domain, we have superimposed all those things. That was second stage. Third stage was ground verification, because of course always we are capturing data from different sources, there may be some mistakes. So just to verify this, okay, a very extensive ground verification was developed at the random locations, and are almost all sort of, like you can see, locations are examined in the field to check whether our database that is captured, it is correct or not. So whatever you can say, because from the remote sensing all data sets, land cover and land use, there's a difference. Land cover is easily captured, but what is the land use? Sometimes we can commit the mistake in land use. Like in a same house, there may be some commercial activities going on, or a building that is located in a residential scheme, it may be using for the commercial domain. Sometimes a particular land was a residence, then it is converted into school or hospital. So such land use differences may be there. So to verify those land uses, essentially ground verification was done, and land use was corrected after the ground verification feedback on a partial level. Okay, then in the fourth stage, basically we have finalized the base map. So after the verification, so first stage is data capturing and GIS database creation. Okay, third stage is superimposition, then preparation of base map, then going into field, verification of land use of all the partials and properties. Okay, then finalization of base map. So that was the fourth step. In the fifth step, the base map or existing situation was superimposed on the master plan. Okay, like master plan, it was for 2035. So 2037, sorry. So it was superimposed, and it was determined what are the changes. Means what are the land use, circulation facilities in the provisions in the master plan, and how existing situation is there, how much deviations are there. Okay, in basically, so the facility gap analysis, it was done here in stage 5, that your existing situation was compared with the master plan, it was compared with the standards. Okay, so first variation was prepared with the master plan, then it was compared with the standards, and then facility gaps are determined on the different scale, on ward scale, on zone scale, and city scale. okay, at a 3 different scale. And then in the next stage, stage 6, okay, the proper adequate provisioning for those gaps, provisionings were done in land uses for different public facilities. Road network was suggested, okay, to facilitate the required norms of circulation spaces to ensure the transport connectivity. Okay, so all those aspects are considered in mind, and appropriate selection of these provisioning of these services are done. Their locations are identified, and a draft zonal plan was prepared. Then it was released for public, you can say, objections and suggestions. After the receiving the public suggestions, okay, it was again re-verified with the existing situation, with the master plan provisions and on the ground, and some objections are you can say declined, some are accepted in this after discussion with the municipality and the representatives. And then final you can say zonal development plans were developed. For zone-wise planning, ward-wise planning was done with respect to facilities, with respect to circulation spaces, with respect to land use provisionings. All those things are done to ensure that that for 2037, all required facilities should be there, development provisioning should be there in each zone. That was done. And in the final, I think it is now in the final approval stages. The zonal plan we have prepared, it is in final stages. So I'm just showing this is the location of Sujangarh. Okay, before that, there's a question on chat box. No, there's no question. Okay. Okay, so this is like demography, connectivity of Sujangarh. And then this is basically urban area. So this this boundary, inside boundary is urbanizable area. Okay, and this is outer one. This is basically peripheral belt. Okay, these are the different zones, A, B, C, D, E, F. These are the different zones. Inside there are A, B, C, D, and outside is E, F. These are the zones. These are the highways and highway development control belts, the plantation belt and controlling belt, all other type of like facilities and type of things which are developed or captured in GIS. Ultimately, they are superimposed. And this is the superimposed, you can say, output for the Sujangarh. Then this is basic introduction. And this is number of villages which are lying in the basically that notified urban area limit of different villages. Then this is demographic details, okay, based on the population of 2011 census. And this is basically brief overview of master plan that was prepared by the planning department. And these are the provisioning of different sort of, you can say, public services in the master plan. And then basically we have like as I explained that we have captured the data, we have created GIS database, we have overlaid, we have calculated the basically defined the planning zones. These are the different ABCD, these are the planning zones, their respective population in different years. Then these are the planning zones. So planning zones are defined based on the connecting like roads, topography, geographical already available zones. So considering all those aspects, further zones were classified. And then data, ultra high resolution data was captured from the drones, so UAVs. So before that, before drone survey, the extensive ground control points were established using DGPS, okay, throughout the city. These are the DGPS points which are accurately using a number of hours of satellite-based readings. Those coordinates were captured and marked on the ground. Then drone was fly and the satellite image was captured. Sorry, drone images are captured from the, so this is the drone image, that is your zone boundaries superimposed on this. Okay, and then in the next we have captured, this is Kasra map. So Kasra map was georeferenced and it was superimposed on the ground. just you can look at it, because Khasra maps are cloth maps, 1:4,000 maps, and they are wear and tear, a lot of, so because georeferencing, number of GCPs are used, but the georeferencing may have some error because your maps may be synced in some corner, uneven shrinkage is there. So some errors were observed in the, but by and large it is satisfactory. Okay, so this is superimposition of Khasra maps. Then this is commitments already made by the council. So those commitment maps are georeferenced and they are translated on your existing situation and checked whether the planned things are existing or not. Like this is the basically the same the commitment that was made, and this is verified on the ground and it is marked on the ground. Okay, then digitization of roads are digitized. Okay, circulation spaces, all roads, all type of you can say railway network. Then this digitization of physical features. Okay, building topologies, like where is the park, where is the water bodies, most of things, open spaces. And so this is the digitization of physical features. And this is existing land use. After detailed, you can say digitization of property level details, capturing of physical features and all. So this is existing land use map. And this was basically verified on the ground. Okay, land use was verified. And this is final existing land use map after ground verification. And these are the different type of existing land use, you can say the provisions are available. So then it was compared with the master plan. Okay, and the gaps were identified in facilities in all these heads, like industrial, mixed, commercial, residential, and then after the finding out the gap with the master plan and the okay, and as per the standards, what is required, then basically as per the government norms, what are the rules and regulations which are notified the government of Rajasthan, those rules are based on those rules, those facility gaps were, you can say, filled with the appropriate provisioning of services in proposed master plan. So this is the gap analysis with the master plan and with the existing one, all type of things are calculated. And then this is after the gap analysis, and we have made a provisions of different sort of services throughout this. Okay, and this is your proposed, you can say, zonal development plan. This was released, and these are the provisioning of the proportion of different type of land use plans, a different type of, you can say, zoning provisions, zone wise provisions. So this is, you can say, after the planning, but after the approval, this is a physical infrastructure, like where are the power lines, where are the road, where is the railway lines. So their proposed roads, all they are there, ensuring the circulation space and all. This is social infrastructure, different type of parks, schools, hospitals, cultural spaces. Those are there was a restriction that has to be all the public services, they need to be planned on public government land. So there are some restrictions. So so in some you can say wards in zones, there are some limitations due to non-availability of government land. This is traffic and transportation network. Okay, missing links and proposed links are there in this. Different type of, like, these are the master plan, zonal plan development proposed roads. Some are master plan proposed roads, and some are we have proposed. So that was the master plan, zonal development plan, that case study we have prepared for this. So this is all from my side, and I hope almost time is over. So still, if you have any questions, I will be happy to answer. Any questions, please?
Any part from architecture, planning, and civil engineering department, you all are requested to kindly, because urban planning and these development plan formulations are basically part of their domain. So you all are requested to kindly participate in the discussion, and you should actually see the physical or the real life example of this Sujangarh area. So all are requested to kindly unmute themselves, whosoever is willing to ask the question. Sir, the question is from my side only. Like the starting phase when we start doing this georeferencing of things in GIS, because there are large number of these custom maps and these like bringing them to a single platform. It might have been very difficult process
Yes,
because
yes, it is.
these, let's say, digitized maps are not available. So this might have been very exhaustive process, and providing and let's say verifying validation of all these things by making, let's say, these what they call locating the ground points. This might have been very expensive. And how many number of people were actually used in this process? May I please know?
You see, yes, yes. In the GIS projects, database creation is consuming 75% of your project time. Plus 75% of time is consumed. But once database is ready, then data analysis is very fast and very easy and very accurate. So in this particular process in georeferencing, it is a very important question that while integrating data from diverse sources, okay, positional accuracy is need to be maintained. Okay, so your georeferencing should be correct at a desired scale. It should be correct. So generally, what we can do is to achieve a certain targeted accuracy, there are standard procedures we have to follow it. That how many number of GCPs you have to adopt. While adopting GCPs, what should be the accuracy? What should be the, like, if you are using a GNSS receivers to capture the GCPs, so for how much time, okay, you are taking reading of satellite so that your positional accuracy should be correct. So all such specifications are formulated in advance. That while capturing this thing, you have to capture these number of GCPs. What is the location as well? Okay, that has to be also determined that, okay, this is the location that we needed. Like your GCPs, they should be well distributed. Okay, what type of mathematical model we are using to fit for georeferencing, that is again the critical decision that we have to make. Okay, so all these aspects are taken care to limit their accuracy within the 1 pixel, like what is the resolution requirement, okay, that was restricted. And of course, a lot of, like in digitization process, like first part, around 6 or 7 like peoples were working, and they had taken around 10 days of time to digitize the first lot of properties, okay, and other type of infrastructure. So a lot of time is required for database creation, and costly as well, because like drone images, capturing drone images, drone survey, it is costly affair. Like now a lot of agencies are available, they do drone survey. They charge around from 11,000 rupees per square kilometer to 20,000 rupees per square kilometer, depending upon what you need, at what accuracy, what resolution, what type of outputs you are requiring.
And sir, was it like the single, let's say, the normal camera was installed on this drone?
No,
or
no.
You have captured other data also, like the thermal and all these things could have been also captured. So have you captured only RGB component or the other?
No, basically it captures the stereo images. Okay, so Z dimension is also generated. That part is also generated. So basically, through the drones, we capture spot heights. We capture the point cloud. From the drones, it is basically, in addition to RGB, it captures the point cloud. Capture X, Y, and Z.
Excuse me, all the participants are kindly.
அது கலர் மாத்தலாமா
கலர் டாப் கலர் மட்டும் மாத்து.
Sir, there is some participant I need to remove.
Black
ஆமா எங்களுக்கு
Okay, so basically point cloud is captured. So in addition to you can say the RGB, the point cloud is captured, that is X, Y, and Z. Okay, so the point cloud and the RGB both are merged together to generate a 3-dimensional digital image. So it doesn't have the thermal, but it is using not a normal camera, a camera, stereo camera that is able to capture the photogrammetric point cloud. मतलब जो शादी ब्याह में यूज करता है वो कैमरा है,
Thank you
that
very
is not
much
used.
for taking your time and delivering the expert lecture on both the topics. Sir, there is one more question
Yeah.
from Pooja Chaudhary. Georeferencing has its limitation. Like when the tool cannot locate a certain address, it automatically, without alerting the user, searches through other geographical levels. How to deal with it?
Please can.
Sir, it's available in chat box. I'm unable to read it. Yeah.
Sir,
Georeferencing has its
limitation. Like okay, let me check. Like when this tool cannot locate a certain address, it automatically, without altering the user's, searches through other geographic levels. How to deal with its limitation when this tool cannot locate a certain. You see, in georeferencing, automatically it doesn't do anything. User has to supply the GCPs. Okay, ground control points, they need to be defined by user. The software automatically doesn't locate the GCPs or locate any position. So we have to capture the GCPs. Now GCPs can be captured from the field, directly from the field using GPS or some satellite positioning solutions, or you can obtain the GCPs from already available reference maps like survey opposites. Okay, and use those GCPs. Now you should ensure that these GCPs, they should be well distributed throughout your image. Then it will be okay. I hope that the question is answered. You can switch on your micro, like phone, and then if you can ask. Voice is breaking. So okay, I'm repeating it. So basically, in georeferencing, the algorithm or software doesn't do anything automatically. Okay, georeferencing is required number of GCPs, and those GCPs need to be captured by the user. Now, GCPs can be observed from the already available maps, georeference maps, or we can go into field.
Sir,
and
the voice is breaking. Maybe due to the signal issues.
Maybe there are signal issues. Okay. So now is it coming?
Sir, it's coming.
Okay, so I was saying that in georeferencing, GCPs need to be collected by user, not it doesn't do anything automatically. Okay, so GCPs user has to capture, either capture from already available georeference maps or from satellite-based positioning solutions like GNSS. But you should ensure that GCPs, they should be well distributed throughout your image. If you have sufficient number of GCPs and they are well distributed, then your georeferencing will be okay.
Sir, there are some signal issues, I feel.
Okay,
so
maybe.
If it's audible from my side, we are very thankful to you for delivering both the sessions on a very lighter note and to the best explanations that I could see. So thank you very much, sir. Thank you very much again for finding the time for delivering the sessions.
Thank you, Bawar sir. Thank you for inviting.
Thank you, sir.
And then always such programs will always useful if we are doing it face to face, so that
Sir, next time we'll be having it face to face only. Bringing it in the online system, it's very difficult to see the participants. There are participants like in my previous report also I have sent it very clearly that these online discussions doesn't happen, and I'll as and when I'll be meeting the member secretary AICT, I'll talk to him also regarding this issue, because it's quite difficult to invite participants and see what participants are doing. All the participants should be asked to like keep their video mode on Just the only procedure that we could take care in the online mode. Otherwise, this is going in vain, because the speakers to the best level of their knowledge are explaining, and the participants are not even uttering a single word. So it's quite difficult to have such kind of participation.
Yeah.
So I'll again discuss with the member secretary and the vice chairman sir also.
No, it's
as and
okay.
when we-
Because this is the situation and we need to deal it. So whatever best we can do, we are doing. All we people are doing.
Yes,
Even participants are
Yes,
also
sir.
doing. So thank you very much for inviting,
Yes,
and
sir.
thank you to all the participants for patient listening. Thank you very much.
Thank you, sir. Thank you very much, sir.
Thank you very much.
Thanks a lot, sir.
To all the participants, it's quite difficult to see and quite like embarrassing when the expert is asking questions rather than asking for discussion. Then none of the participants basically tries to like participate in discussions. That will be reported, no doubt. And there are people who are not even aware of whether their mic is on or off. It's also again, I again request you all to kindly take care of your videos and mics. So unmute yourself only when it is required to ask questions or fall in discussion with the expert, rather than unnecessarily putting your mics on. So I request you all again to join back at 2:30.